Tonight, we are traveling to the deepest reaches of our planet, a place where the rules of life begin to bend under weight and darkness. This is the world below the light. Humans have explored less than 0.01% of the deep ocean, yet nearly every descent returns with the same quiet contradiction that as conditions grow harsher, life does not retreat into smaller forms. As sunlight disappears, temperatures fall toward freezing, food thins into drifting fragments, and pressure rises high enough to crush steel. Biology predicts that survival should favor simplicity and restraint. Instead, in these narrowing conditions, bodies often grow larger, slower, and more extreme, as if responding to a rule we never expected to find. These environments remain permanently cold, low in oxygen, and locked beneath crushing weight, places where classic biology expects collapse. Limited energy should restrict growth, and pressure should enforce limits. Yet, time after time, observations reveal life expanding beyond those expectations. In the deep ocean, depth replaces distance. Each descent rewrites the conditions of survival. Near the surface, photosynthesis anchors food webs, and size remains constrained by speed, predators, and light. But deeper down, as the sunlit world slips away, early signs appear that the old limits no longer apply. In the twilight and beyond, vision begins to fail, eyes grow larger, bodies stretch longer, and efficiency quietly replaces speed. The deeper we go, the more often scientists note the same unsettling pattern, that size keeps increasing where survival should narrow, as though the ocean itself is guiding life toward scale rather than restraint. But why does life grow larger where biology predicts it should fail? What unseen advantage does size offer in the cold and crushing dark? How deep does this pattern extend beyond the reach of our instruments? And how many giants exist in places we have never touched? Tonight, we will drift gently through the layers of the ocean, listening closely to what depth itself seems to be telling us. But before we begin, if you enjoy videos like this, slow, soothing, and quietly filled with wonder, I'd love it if you gave this one a gentle like and maybe tapped subscribe. It helps more curious minds like you find their way to this peaceful little corner of the internet and lets the algorithm know that sleep and science go perfectly together. And if you'd be so kind, let me know in the comments where you are winding down from tonight and what time it is there. It's always a joy to see how far across the world this little sleepy corner of science travels. Now take a deep breath, let your shoulders loosen, close your eyes, and together let us sink slowly into the vast quiet beneath the waves. The ocean, from the surface, appears whole, a single skin of moving water stitched together by tides and wind, reflecting the same sky wherever it touches land. For much of human history, this illusion of sameness shaped how we imagined what lay below. We spoke of the sea as one place, vast but uniform, as though depth were only a matter of distance from shore. But the ocean is not arranged like a map, it is arranged like a descent. What truly divides the sea is not latitude or longitude, but depth. With every slow movement downward, the environment reshapes itself, not suddenly, not violently, but patiently, layer by layer, as if the planet were revealing its inner thoughts, one breath at a time. Near the surface, the ocean still remembers the sun. Light pours through the upper water, fractured into shifting patterns, feeding drifting life and setting daily rhythms. Temperature rises and falls with weather and season. Food is renewed constantly, born from sunlight and motion. Here the sea feels alive in familiar ways, restless and bright, stitched tightly to the world above it. But depth changes everything, and it does so quickly. Light weakens first, colors thin and then disappear, red fading before blue, until even blue becomes only a suggestion. Shadows stretch longer, then lose meaning altogether. Vision, once reliable, begins to falter. What was once seen must now be sensed. Pressure follows, building steadily, invisibly. Each step downward adds weight, not felt as force but as presence. Water presses inward from every direction, reshaping what can exist, how cells hold together, how structures endure. Nothing escapes it, nothing resists it outright. Life learns instead to yield, to flex, to persist without rigidity. Temperature settles into stillness. The ocean's surface may warm and cool, but the depths remain almost unchanged, hovering near freezing, year after year, century after century. Time moves differently here. Chemical reactions slow, growth stretches across longer spans, change becomes subtle, deliberate, and food, which once arrived in abundance, becomes an event rather than a constant. Energy drifts downward in fragments, a snowfall made of remnants, a slow rain of what the surface can spare. Nothing is wasted, nothing arrives quickly. Because of this, depth matters more than distance ever could. Two creatures separated by thousands of miles, but living at the same depth, often share more in common than neighbors stacked only a few hundred meters apart. The ocean connects horizontally with currents and migrations, but it divides vertically with far greater authority. Each layer becomes its own world, shaped by a specific balance of light, pressure, cold, and scarcity. As the descent continues, the boundaries between these layers become more pronounced. The sea stops behaving like a single environment and begins to resemble a series of stacked realms, each quieter than the last. Motion slows, sounds soften, the water grows heavy with stillness. What is remarkable is not that life changes in response, but how precisely it does so. The ocean does not impose chaos, it imposes gradients, gentle, unbroken slopes of condition that guide adaptation rather than forcing it. Life does not leap from one form to another. It drifts, gradually reshaped by the long patience of depth. In this way, the ocean becomes less a place and more a process, a continuous transition from light to darkness, from warmth to cold, from abundance to restraint. Each vertical zone holds its own logic, its own quiet rules, written not in lines, but in pressure and time. Understanding the deep ocean begins here, not with creatures or extremes, but with the realization that depth itself is the architect. Distance tells us where we are on the surface of the world. Depth tells us which world we are in. And once this becomes clear, the descent no longer feels like a journey downward. It feels like a passage inward, into environments that grow stranger, not because they are hostile, but because they are consistent in ways we rarely experience above. The ocean is not one place. It is a layered story, told slowly, downward, where every meter rewrites what survival means, and where the quiet changes matter far more than the dramatic ones. The descent begins almost without notice. After the layered understanding of depth settles in, the ocean's uppermost world still feels close, familiar, gently alive. This is the realm that remains tied to the sky above it, where sunlight reaches freely and the water carries the memory of day and night. Scientists call this layer the epipelagic zone, but it can be imagined more simply as the ocean's breathing skin. Here, light does more than illuminate, it feeds. Sunlight filters down through moving water and becomes energy, captured by drifting life so small it is almost invisible. Microscopic plants float and turn light into living matter, quietly forming the foundation of nearly everything that follows. Fish, larger plankton, and swift predators all depend on this steady conversion of light into food. Nothing here exists in isolation. Every movement is connected to that original exchange between sun and sea. Because energy is renewed constantly, life gathers densely in this upper layer. It is not because the surface is safer, but because it is productive. Meals arrive regularly, growth can happen quickly, reproduction becomes frequent. The water is never still for long, stirred by wind, waves, and currents that mix warmth and nutrients together. Motion defines this world. Even rest is temporary. In this bright layer, the ocean feels busy. Bodies flash and turn, schools form and dissolve. Color matters. Vision guides survival. Speed decides who eats and who escapes. The pace of life is fast enough that stillness becomes risky. To hesitate too long is to fall behind the rhythm that governs everything here. This constant motion places quiet limits on size. Large bodies require steady fuel. They demand continuous intake to support muscle, heat, and movement. Near the surface, where competition is relentless and predators are alert, carrying too much mass becomes a burden. Bigger bodies turn slower. They need more food. They cannot disappear into small spaces or change direction as easily. In a world where danger arrives quickly and from many angles, agility often outweighs strength. As a result, size near the surface settles into a balance. Animals grow only as large as they can reliably sustain. The ocean allows giants here, but only a few, and only those capable of endless movement and constant feeding. For most life, smaller forms thrive. They slip through water efficiently, reproduce quickly, and recover faster from loss. Energy flows rapidly through them, mirroring the restless surface itself. Temperature also plays a role. Sunlit water warms and cools with weather and season. These shifts accelerate metabolism. Chemical reactions happen faster. Growth speeds up, but so does exhaustion. Larger bodies struggle to shed excess heat or adapt quickly to change. Smaller ones respond more easily, their internal processes adjusting to the shifting environment around them. The epipelagic zone, then, is not a gentle cradle. It is an arena shaped by abundance and pressure at the same time. Life here is rich, but it is rarely slow. It demands attention, awareness, and constant motion. Every advantage is temporary. Every mistake is visible. As the descent continues downward, this world does not end abruptly. It thins, light weakens, colors soften. The frantic urgency of the surface begins to loosen its grip. The rules that held size in check start to relax, not because life becomes easier, but because the environment stops rewarding speed above all else. The sunlit world fades behind like a remembered shoreline. Its brightness lingers for a while, filtered and scattered, before finally slipping away. What remains below is shaped by different priorities, where patience replaces haste, and endurance begins to matter more than constant motion. The first drop is gentle, but its meaning is profound. Leaving the sunlit world is not simply a movement downward. It is a passage away from abundance, away from urgency, and away from the tight limits that light and motion quietly impose. The ocean does not fall into darkness all at once. After leaving the bright restlessness of the surface, there is a long, quiet middle where light still exists but no longer rules. This is the twilight zone, known to science as the mesopelagic layer, a place suspended between what can be seen and what must be sensed. Here, sunlight arrives tired. It slips downward in thinning sheets, scattered and bent by water until it loses its warmth and clarity. Colors fade in a gentle order. Reds disappear first, then yellows, leaving the world washed in deep blues and soft grays. Shapes remain visible, but their edges blur. Distance becomes harder to judge. Vision, once dependable, grows uncertain. The rhythm of life slows accordingly. Day and night still exist, but their contrast weakens. Shadows no longer sharpen, time stretches. This is not darkness, but it is no longer light in any familiar sense. In this half-lit world, the first quiet changes in form begin to appear. Bodies start to look slightly unfamiliar. Fins lengthen, torsos narrow or stretch, mouths grow wider in relation to the head. These shifts are subtle, almost easy to overlook, but together they signal something important. The environment is beginning to reward different solutions. Energy here is less predictable. Food still arrives, but not in steady waves. Some of it drifts down from above, fragments loosened from the surface. Some arrive suddenly, carried by migrating animals that move upward at night and sink back into depth by day. Meals become opportunities rather than guarantees. Because of this, bodies begin to adapt for efficiency rather than speed. Many animals grow larger eyes, not for sharp vision, but for sensitivity. The goal is no longer detail, but detection. A faint glimmer of movement, a brief pulse of bioluminescence, becomes enough to signal life nearby. Seeing first matters more than seeing clearly. Alongside these visual changes, proportions begin to shift. Some creatures develop longer limbs or extended sensory structures, increasing their reach without demanding constant motion. Others grow softer, their bodies yielding gently to pressure and conserving energy. Movement becomes measured. Nothing here is wasted. Scientists first noticed these patterns not in a single species, but across many unrelated ones. Fish, crustaceans, and gelatinous organisms all showed similar adjustments as they entered this zone. Different lineages, shaped by different histories, were arriving at comparable solutions. Depth was beginning to guide form in a consistent direction. The twilight zone also marks a quiet turning point in how size functions. Near the surface, larger bodies faced constant pressure from competition and speed. Here, those pressures ease slightly. Predators are fewer, encounters are less frequent. The environment becomes more forgiving of patience. This does not mean life becomes easier. Scarcity still exists, but the balance shifts. Carrying a bit more mass can help store energy between meals. Longer bodies can glide rather than dart. Slower metabolisms reduce the cost of waiting. The strict size limits imposed by the surface begin to loosen, not dramatically, but noticeably. Temperature continues its gradual decline, settling into a narrower range. Seasonal swings fade. Stability replaces variability. In this steadier environment, rapid growth becomes less important than endurance. Life no longer needs to respond instantly to every change above. It can afford to slow down. The mesopelagic zone, then, becomes a place of transition in every sense. Light weakens but does not vanish. Movement slows but does not stop. Familiar shapes persist, but they stretch and soften at the edges. It is a world learning how to function without certainty. For researchers, this layer offered the first clues that depth itself was shaping biology in ways surface rules could not explain. The patterns were too widespread to dismiss. Something about reduced light, increasing pressure, and uncertain food was nudging life toward different forms, gently rewriting what survival looked like. As the descent continues, the twilight thins further. The last usable light dissolves into a uniform dimness. Vision prepares to surrender its dominance. The ocean grows quieter, heavier, and more patient. The rules are not broken here. They are simply changing, one subtle adjustment at a time, as life follows the fading glow downward into deeper water. As the last traces of reliable light thin and dissolve, life does not collapse into confusion. Instead, it begins a careful reorganization. Vision, once the dominant guide, slowly loosens its hold, not because eyes fail all at once, but because light no longer offers enough certainty to justify dependence on it alone. In this deeper water, shapes are no longer outlined by brightness. Contrast softens, distance becomes ambiguous. An object may be near or far, moving or still, and the difference is no longer obvious at a glance. Under these conditions, vision becomes expensive. Maintaining sharp sight demands constant energy, and energy here is no longer freely available. Life responds not by abandoning sight, but by reshaping it. In many species, eyes grow larger, not to see more detail, but to gather more of what little light remains. A larger eye works like a wider window, allowing faint traces to enter that would otherwise be lost. Even a single particle of light, released by drifting bioluminescence, can become meaningful when captured by a broad, sensitive surface. These eyes are less about clarity and more about presence. They notice rather than inspect. At the same time, other senses begin to rise quietly into prominence. Touch becomes more important, carried through extended fins, trailing filaments, or delicate hairs that register subtle changes in water movement. Pressure waves replace visual cues. The faint displacement of water becomes a form of awareness, allowing life to detect motion without ever seeing its source. Chemical sensing also grows more refined. In darkness, scent travels farther than sight. Molecules linger, spreading slowly through still water. Some animals learn to read these traces, following invisible pathways left behind by food, by rivals, or by distant gatherings of life. The ocean becomes a landscape written not in light, but in chemistry. Sound, too, begins to matter more. Not loud sound, but vibration. Low-frequency pulses travel efficiently through water, bending around obstacles and crossing long distances. Bodies tuned to these movements can sense the presence of others long before contact occurs. Communication becomes quieter, slower, and more deliberate. As these sensory systems strengthen, speed loses its central role. Chasing becomes inefficient when targets are rarely seen and energy must be conserved. Rapid bursts of motion give way to long periods of stillness. Life learns to wait. Energy efficiency begins to shape every aspect of survival. Muscles are used sparingly. Movement is planned rather than reactive. Many animals drift rather than swim, allowing currents to carry them through space without cost. Others settle into slow patrols, covering territory patiently rather than aggressively. This shift has consequences for body design. Slower lifestyles allow for softer forms. Rigid skeletons become less necessary when sudden acceleration is no longer required. Flexible tissues adapt more easily to pressure and require less maintenance. Bodies grow elongated or widened in ways that favor stability and glide rather than speed. Larger size, in this context, begins to make sense. Bigger bodies store energy more effectively and lose it more slowly. They provide space for larger sensory organs, wider eyes, longer feelers, and expanded chemical receptors. Size becomes a platform for efficiency rather than power. None of these changes happen abruptly. They accumulate over generations, guided by the quiet arithmetic of survival. Every trait that reduces unnecessary movement, every adjustment that lowers energy demand, becomes valuable. Over time, the ocean fills with forms that appear unhurried, even tranquil, yet finely tuned to their environment. Darkness does not simplify life, it refines it. Without constant visual stimulation, the deep ocean becomes a place of heightened sensitivity. Life there is aware in different ways, attentive to signals that surface creatures rarely notice. A slight change in pressure, a faint vibration, a trace of chemistry carried on a slow current. These become the language of survival. In this world, speed is no longer a universal advantage. Endurance matters more. Precision matters more. The ability to persist through long stretches of stillness becomes a strength rather than a weakness. As depth increases, the reshaping continues. Vision remains, but it is no longer alone. It is supported, supplemented, and sometimes surpassed by other senses better suited to the quiet weight of darkness. Life does not retreat from the absence of light, it adapts into it, folding darkness into its design and learning how to live not by racing through space, but by listening closely to the water itself. As the descent continues beyond the last reach of useful light, the ocean settles into a different kind of vastness. The water grows heavier and quieter, not with motion, but with scale. This is the abyssal plain, a region so expansive that its size is difficult to hold in the mind. It stretches across the sea floor in broad, gentle contours, covering more area than all the continents above combined, yet hidden beneath kilometers of water and time. Here, darkness is complete, not the dimness of fading light, but a steady absence that never lifts. Day and night no longer pass overhead. The surface world, with its shifting brightness and weather, feels distant and abstract. The abyss exists outside of those rhythms, wrapped in unbroken shadow. Temperature changes little here. The water remains near freezing, held in a narrow range that barely shifts across centuries. There are no seasons in this depth, no warming sun, no cooling winds. The environment is remarkably stable, and that stability slows everything. Chemical reactions proceed at a measured pace. Growth stretches over long spans. Movement becomes deliberate. Pressure presses in from all sides, constant and immense, but life no longer reacts to it as a threat. By this depth, survival depends on yielding rather than resisting. Bodies are shaped to endure without rigidity, to function under weight that would flatten anything unfamiliar with such conditions. For a long time, humans believed this world to be almost empty. Early expeditions dragged nets across the deep seafloor and returned little. The samples were sparse and broken, instruments failed, cameras struggled in the dark. From these fragments, scientists formed a picture of the abyss as a biological desert, too cold, too dark, and too starved of energy to support much life. This assumption made sense, given what was known at the time. Food arrives here slowly, falling from above in scattered particles. No sunlight penetrates. Energy input is minimal and irregular. By surface standards, this seemed incompatible with abundance. What those early views missed was time. The abyssal plain does not function on the same tempo as the upper ocean. Life here is not built around constant input, but around persistence. Small amounts of energy, arriving steadily over immense spans, accumulate. Nothing is wasted. Every fragment that settles becomes part of a slow, careful economy. As exploration improved, the picture began to change. More sensitive instruments revealed movement where stillness was expected. Tracks crossed the soft sediment. Burrows marked the seafloor. Soft-bodied organisms emerged in camera lights, then faded back into darkness. The abyss was not empty, it was patient. The seafloor itself plays a role in this quiet productivity. Fine sediments blanket the plain, creating a stable surface for life to anchor, burrow, and feed. Microbial communities work continuously, breaking down organic material and recycling nutrients. Larger animals move slowly across this landscape, conserving energy, feeding selectively, and enduring long intervals between meals. The vastness of the abyssal plain also changes how life spreads. With so much continuous habitat, populations can exist at low densities yet remain stable over time. Encounters between individuals are rare, but not necessary for survival on short timescales. Reproduction slows, lifespans lengthen, the urgency seen near the surface dissolves. In this environment, size begins to take on a different meaning. Larger bodies can travel farther between feeding opportunities. They store energy more efficiently. They move through the cold with less relative loss. Over long periods, these advantages accumulate, quietly shaping which forms persist. The abyssal plain does not announce its richness, it hides it in stillness and scale. Its life is not crowded into reefs or flashing schools. It is spread thin across immense distances, woven into the sediment and water, present everywhere and nowhere at once. What once appeared lifeless was, in truth, simply slow. As the descent settles into this deep, level world, the ocean feels less like a series of dramatic thresholds and more like a long, steady continuation. Darkness remains, cold remains, pressure remains. And within these constants, life continues to adapt, not through speed or abundance, but through endurance, patience, and time. The abyssal plain stretches on beneath the water, quiet and immense, holding more living space than any other place on Earth, and reminding us that absence of motion is not absence of life. By the time life settles fully into the deep, the ocean has taught patience. The hurried exchanges of the surface feel distant now, replaced by long stretches of stillness where nothing arrives for days, sometimes longer. In this quiet, food is no longer a constant presence. It becomes a rare visitor. Most nourishment in these depths comes from what scientists call marine snow. It is not snow in the way the surface knows it, but a slow, drifting fall of fragments, tiny pieces of organic matter loosened from life above. Remains of plankton, discarded shells, fecal pellets, and the soft debris of creatures that lived and died far overhead. These particles settle gradually, spiraling downward through the water column, thinning as they fall, spreading across immense distances. When marine snow reaches the abyssal plain, it arrives gently. There is no rush. Each fragment is small, often barely visible, but together they form the foundation of deep ocean life. This steady drizzle feeds microbes first. Bacteria and other microscopic organisms break down the material, releasing nutrients back into the sediment and water. From there, energy moves upward through the food web, slowly, carefully, without waste. Because this supply is constant but sparse, meals are unpredictable. There may be long intervals with little to find, followed by brief moments of abundance when currents shift or larger pieces settle from above. Life here is shaped not by how much food exists, but by how long one must wait between meals. For a long time, it seemed logical to assume that such scarcity would favor small bodies. Smaller animals need less energy. They can survive on fewer resources. This reasoning holds true in many environments, especially those where food arrives frequently but in limited amounts. Yet, in the deep ocean, the pattern bends in a quieter direction. Infrequent feeding changes the equation. When meals are rare but significant, the ability to store energy becomes more valuable than the ability to eat constantly. Larger bodies provide space, space for fat reserves, space for slower metabolisms that stretch each intake across long spans. Size allows energy to be banked rather than spent immediately. A larger animal can endure longer periods of hunger without physiological stress. Its tissues lose energy more slowly. Its internal systems are buffered against sudden scarcity. In contrast, very small bodies burn through reserves quickly. When food disappears, they have little margin for error. Movement also matters. Searching for food across vast, dim landscapes costs energy. Larger bodies travel more efficiently through cold water. They maintain momentum with less relative effort. Each movement carries them farther per unit of energy spent. Over time, this efficiency compounds. This does not mean that every deep sea animal grows large. Instead, it means that size, once seen as a liability under scarcity, becomes a form of insurance, not against predators, which are relatively rare at these depths, but against time itself, against the long waiting periods that define survival here. Even behavior adapts around this reality. Many deep sea creatures feed opportunistically, consuming whatever arrives and storing what they can. Some feed rarely, but when they do, they feed extensively. Others rely on slow digestion, extracting maximum value from minimal intake. Nothing is rushed, nothing is wasted. Occasionally, the ocean delivers a larger gift: a fallen carcass, a drifting mass of organic matter, or a sudden accumulation of marine snow. These events do not last long, but their impact echoes. Larger animals are better equipped to exploit these moments fully. They can consume more, store more, and survive longer afterward. Over evolutionary time, this rhythm shapes bodies. Size becomes less about dominance and more about endurance. A quiet adaptation to an environment where patience matters more than speed and waiting matters more than winning. The myth of small bodies in the deep dissolves under this logic. Scarcity does not always reward minimalism. Sometimes it rewards capacity, the capacity to endure long silences between meals, the capacity to hold on to energy and stretch it across weeks, months, or longer. In the deep ocean, food scarcity does not shrink life into fragility, it reshapes it into resilience. Size becomes a buffer, a slow and steady answer to an environment where nourishment arrives softly, drifts slowly, and asks those who depend on it to wait. As the descent continues, another presence becomes impossible to ignore. It does not flicker like light or drift like food. It does not arrive suddenly or leave again. It is always there, pressing evenly from every direction. Pressure is the ocean's most constant companion, growing heavier with each passing depth, shaping life not through forceful moments, but through unending presence. Pressure in the deep ocean is not a blow, it is a weight that never lifts. Water presses inward on every surface, on every gap, on every living cell. To anything unfamiliar with it, this weight would be overwhelming. Structures would collapse, spaces would vanish. Yet for deep sea life, pressure is not an enemy to be fought. It is a condition to be understood and woven into existence. At the smallest scale, pressure reaches into cells themselves. It alters how molecules sit together, how proteins fold, how membranes hold their shape. Proteins, the working machinery of life, rely on precise forms to function. Under increasing pressure, those forms can distort, threatening the reactions that keep cells alive. Membranes, the delicate boundaries that separate inside from outside, can stiffen or leak if their balance is disrupted. Deep sea organisms respond not with brute strength, but with chemistry. Their proteins are built slightly differently, tuned to remain flexible under weight. Their cellular machinery continues to move and interact, even when pressed by forces that would silence surface life. Enzymes function steadily, neither rushed nor stalled, maintaining life's quiet rhythm. Membranes, too, adapt. The fats that form them are arranged to stay fluid in cold, high pressure environments. Instead of becoming rigid and brittle, they remain gently pliable, allowing nutrients to pass and signals to travel. The boundary between cell and sea stays intact, responsive rather than resistant. These changes are not dramatic when seen individually. They are subtle adjustments, accumulated over generations, refining life at a molecular level. Pressure does not demand armor, it demands harmony. For a long time, scientists believed that pressure alone must limit size. The logic seemed sound. Greater size meant more internal structure, more spaces that could collapse, more systems vulnerable to stress. It was assumed that beyond a certain point, large bodies would simply fail under their own complexity. But observation began to tell a different story. Once life solves the biochemical challenges of pressure, size itself becomes less constrained. Pressure acts equally on all parts of a body, inside and out. There is no crushing force from above, no uneven load to bear. For organisms adapted to it, pressure becomes neutral. It is present, but no longer harmful. What matters more is whether tissues remain flexible and chemistry remains stable. When those conditions are met, growing larger does not multiply the danger. A bigger body experiences the same pressure as a smaller one at the same depth. The difference lies not in weight, but in design. In fact, larger bodies can sometimes benefit from pressure-adapted chemistry. Their tissues are often softer, more hydrated, and more evenly supported by surrounding water. Internal spaces are reduced or filled with fluids that compress predictably. There are no rigid air-filled cavities to collapse. Everything yields together. This realization quietly reshaped how scientists viewed deep-sea gigantism. Pressure was no longer seen as a hard ceiling. Instead, it became part of the background, a constant condition that life could fully integrate into its biology. Rather than limiting growth, pressure encourages certain forms of efficiency. Slow metabolisms pair well with stable chemistry. Soft tissues pair well with even compression. Large size pairs well with long lifespans and reduced urgency. Together, these traits form bodies that do not fight their environment, but rest within it. The deep ocean does not reward resistance, it rewards accommodation. Pressure, once imagined as a crushing barrier, reveals itself as a sculptor. It trims away designs that rely on rigidity and haste. It favors flexibility, patience, and internal balance. When life meets these conditions, size becomes a variable once more, shaped by food, energy, and time rather than fear of collapse. As the descent continues, pressure remains unchanged in its presence. It does not intensify suddenly, it simply accumulates. And life, adjusted at its smallest scales, continues onward, carrying its growing forms deeper into the dark, untroubled by the weight that once seemed impossible. By now, the ocean has grown quiet in a way that feels deliberate. Motion still exists, but it is no longer constant. It appears only when necessary, then dissolves back into stillness. This is the rhythm of slow-motion ecosystems, where life has learned that movement carries a cost, and stillness can be a form of survival. In the deep, energy is never wasted. Every shift of muscle, every turn of the body, requires fuel that may not be replaced for a long time. Food arrives irregularly, and the distance between meals stretches wide. Under these conditions, constant movement becomes an unnecessary expense. The ocean does not reward those who search endlessly. It favors those who wait. As light fades and pressure settles into permanence, the environment grows stable in temperature and chemistry. There are no sudden storms, no shifting tides, no rapid changes that demand quick responses. With so little variation, speed loses its value. There is rarely a need to flee, to chase, or to react instantly. Instead, life becomes tuned to anticipation rather than action. Many deep sea animals drift rather than swim. They allow currents to carry them slowly across space, conserving energy as they go. Others remain nearly motionless, anchored to the seafloor or hovering just above it, their bodies poised in quiet readiness. Movement is saved for moments that matter, when food passes close enough or when a rare encounter unfolds. This restraint shapes bodies in subtle ways. Muscles are built for endurance rather than bursts of power. Movements are smooth and economical, avoiding sharp turns or rapid acceleration. Fins and limbs become tools for balance and gentle propulsion, not speed. Within this slow world, larger bodies gain an unexpected advantage. As organisms increase in size, their energy needs do not rise in simple proportion. A larger body uses less energy per unit of mass than a smaller one. Heat is lost more slowly. Metabolism can run at a lower pace. Each calorie stretches farther. This principle changes how survival works in the deep. A larger animal can move less often without suffering. It can wait longer between meals. It can afford to remain still while the environment drifts past. Size becomes a way to smooth out scarcity, spreading energy use over time rather than consuming it all at once. Patience, in this context, is not passive. It is an active strategy refined over generations. Waiting allows the ocean to deliver what it will. Marine snow settles, carcasses sink, currents shift. Those who endure long enough are present when opportunity finally arrives. In slow motion ecosystems, interactions unfold gradually. Predators do not sprint. They approach carefully or rely on ambush, minimizing effort. Prey do not flee frantically. They rely on concealment, endurance, or simple absence. Encounters are rare, and when they happen, they are deliberate. This pace reshapes behavior as much as anatomy. Reproduction slows. Growth extends across years, sometimes decades. Life history becomes stretched and deliberate, synchronized with an environment that changes little from day to day. There is no advantage to haste when the future looks much like the present. Even communication reflects this calm. Signals are subtle. Bioluminescent flashes are brief and measured. Chemical cues spread slowly through the water. Everything speaks softly, conserving energy while remaining aware of what surrounds it. From a distance, this world can appear empty or inactive. Early observers mistook stillness for absence, silence for lifelessness, but beneath that calm lies a system finely tuned to endurance. Every organism plays its part in a long, patient cycle where survival is measured not in speed, but in time. The advantage of patience becomes clearer with depth. Those who rush burn out, those who wait persist. Over evolutionary time, this preference shapes ecosystems that function more like a steady heartbeat than a pulse, slow, reliable, and resilient. As the ocean deepens, this rhythm continues to assert itself. Life moves less, grows slower, and lasts longer. The world becomes quieter, but not poorer. Instead, it grows deliberate, shaped by the understanding that in the deep, the greatest success belongs to those who know when not to move. And so the descent carries on through a living landscape defined by stillness, where energy is guarded carefully, Size becomes a tool for efficiency, and patience proves itself as one of the ocean's most powerful adaptations. By the time the descent reaches its steady rhythm, a quiet pattern begins to stand out. It is not loud or sudden, and it does not belong to a single creature or place. It appears gradually across many depths and many forms, revealing itself only after long observation. This pattern is known as deep sea gigantism, a tendency for certain organisms living far below the surface to grow noticeably larger than their close relatives in shallower waters. Deep sea gigantism is not a rule written into one branch of life. It is a repeated outcome. Crustaceans, worms, jelly like animals, and even some fish show versions of it. Familiar shapes return, but scaled up, stretched, or thickened in ways that feel unexpected when compared to their surface counterparts. The same basic body plans persist, yet they occupy more space, move with heavier presence, and carry more mass than their relatives closer to the light. This idea did not emerge all at once. Early deep sea expeditions brought back strange specimens that seemed exaggerated, oversized versions of known animals. At first, these finds were treated as curiosities. The deep ocean was still poorly understood, and many believed these large forms were rare accidents rather than part of a broader pattern. As exploration continued and sampling improved, the pattern became harder to ignore. Again and again, researchers found that species collected from greater depths tended to be larger than those from shallower environments. This was not limited to one region or one lineage. The same trend appeared in different oceans, under different conditions, separated by vast distances and long evolutionary histories. Over time, scientists began to recognize deep sea gigantism as a genuine biological phenomenon. It was not a quirk of sampling or a handful of unusual species. It was a signal that depth itself was shaping size in a consistent way. What makes this pattern especially striking is how often it appears across unrelated groups. Animals with no close evolutionary connection arrive at similar outcomes. A crustacean and a worm, separated by hundreds of millions of years of evolution, can both become larger in the deep. This convergence suggests that the environment is guiding form more strongly than ancestry. The reasons lie in the slow, steady pressures described earlier. Scarce food favors bodies that can store energy. Cold, stable temperatures support slower metabolisms. Pressure, once accommodated at the cellular level, does not punish growth. Reduced predation lowers the cost of being large. Together, these conditions create an environment where increasing size becomes not only possible, but useful. Deep sea gigantism does not mean unchecked growth. It is selective. Only certain forms benefit from it. Animals that rely on speed, rapid reproduction, or frequent feeding do not follow this path. But for those adapted to waiting, conserving, and enduring, larger size offers advantages that accumulate over time. History shows that recognition of this pattern required patience, much like the environment itself. Early scientists lacked the tools to see the deep ocean clearly. Many organisms were damaged during collection, their true proportions distorted or lost. Fragile giants escaped notice entirely. Only with gentler sampling methods and extended observation did the scale of the pattern come into focus. As understanding grew, deep sea gigantism began to shift how biologists thought about size limits in general. It challenged the assumption that harsh environments always force life to become smaller. Instead, it revealed that stability, even under extreme conditions, can open the door to growth in unexpected directions. The deep ocean does not encourage gigantism through abundance. It encourages it through consistency. Long spans without disruption allow slow strategies to succeed. Size becomes a way to smooth out uncertainty, to buffer against scarcity, and to stretch survival across time. Seen this way, deep sea gigantism is less about becoming huge and more about becoming durable. It reflects an environment where the future is predictable enough that waiting makes sense, and where the slow accumulation of advantage matters more than quick success. As the descent continues, this pattern remains present in the background, quietly shaping the forms encountered along the way. It is not dramatic or monstrous. It is measured, repeated, and deeply rooted in the physics and chemistry of the deep. Deep sea gigantism stands as one of the clearest signs that the deep ocean follows its own logic, a reminder that life does not always shrink when conditions grow severe. Sometimes, when the world grows quieter and time stretches long, life grows larger instead. As the descent carries deeper into the quiet logic of size, one shape begins to feel strangely recognizable: flattened body, segmented shell, many jointed legs moving in slow coordination. At first glance, it resembles something that might scuttle beneath a rock along a shoreline, something small, quick, and easily overlooked. But here, in the abyss, the scale is different. Giant isopods carry the same basic design as their shallow water relatives, yet they occupy the deep with an entirely different presence. What lives near coasts and coral rubble rarely grows larger than a hand. What lives far below expands into a form that fills the water with weight and stillness. Familiar anatomy, enlarged patiently over time. This similarity is important. It tells us that giant isopods are not a separate invention of the deep. They are an extension of an existing plan, reshaped by environment rather than rewritten by chance. The same body that works in tide pools is carried downward, adapted step by step, until it becomes something that feels both known and unfamiliar. Near the surface, small isopods live fast lives. They feed often, reproduce quickly, and remain in constant motion to avoid predators. Their small size allows them to hide, to slip into cracks, to disappear when danger arrives. Energy flows quickly through their bodies, burned and replaced in rapid cycles. In the abyss, this rhythm would not work. Food does not arrive often enough to sustain constant activity. Hiding places are fewer, encounters are rare. Instead of speed, survival favors endurance. Giant isopods meet this demand by slowing almost everything about themselves. Their metabolism runs low and steady. Chemical reactions unfold at a measured pace. Muscles are used sparingly, not built for bursts, but for brief, deliberate movement. Much of the time, they remain still, resting on the seafloor or drifting slightly above it, conserving energy while the dark stretches on. This slow pace extends across their entire lives. Giant isopods grow gradually, over many years. Their lifespans stretch far beyond those of their shallow relatives. Time becomes less urgent in an environment where change itself is rare. Size supports this strategy in quiet ways. A larger body holds more stored energy. Fat reserves can be built slowly when food appears, then drawn upon during long periods of absence. When marine snow thins or nothing falls for weeks, the isopod does not need to move. It can wait. Digestion itself becomes part of this patience. Giant isopods are known to feed heavily when opportunity arises, consuming far more than they immediately need. Their systems are designed to process and store these rare meals efficiently, stretching each event across long spans of time. This is where their size reveals its true purpose. It is easy to imagine that growing large in the deep might serve as protection from predators. But in the abyss, Predators are not the primary threat. Encounters are infrequent, and many predators rely on ambush rather than pursuit. Speed and armor matter less here than they do near the surface. Starvation is the greater danger. Size protects giant isopods not by making them untouchable, but by making them resilient. Larger bodies lose energy more slowly. Their internal systems remain stable through long periods of scarcity. They do not need to feed often, only effectively. Even their hard outer shell, while offering some defense, plays a subtler role. It reduces water loss, supports internal pressure balance, and provides structure without demanding constant repair. It is not built for combat, but for persistence. Seen this way, giant isopods become a clear expression of deep sea logic. They are not aggressive giants, they are patient ones. Their size reflects an environment where waiting is rewarded, where stillness is safe, and where endurance carries more value than speed. When researchers first encountered these animals, their scale seemed startling, even unsettling. A shape so familiar, yet so large, challenged expectations. Over time, that surprise softened into understanding. The giant isopod is not an exception, it is a lesson. It shows how a simple body plan, placed into a slow, stable, and resource-limited world, can expand rather than shrink. It shows how size, when paired with patience, becomes a quiet solution to one of the deep ocean's greatest challenges. In the dim stillness of the abyssal plain, giant isopods move rarely, feed rarely, and live long lives measured not by urgency, but by time. Their familiar shape carries an unfamiliar message. In the deepest parts of the ocean, survival does not belong to the fastest or the fiercest. It belongs to those built to wait. As the descent leaves the broad calm of the abyssal plain, the seafloor begins to break and fold. Smooth expanses give way to long slopes that drop sharply into narrow valleys. These are the hadal trenches, the deepest places on Earth, carved slowly by the movement of tectonic plates and held open by immense pressure and time. It was here, in these extreme depths, that scientists encountered something quietly astonishing. Amphipods, small crustaceans, usually no larger than a finger near the surface, appeared at sizes that felt almost unreal. Some were large enough to fill the frame of a camera. Their bodies were thick, muscular, and pale, drifting and crawling through darkness that had never known light. The discovery did not come all at once. Early glimpses were fleeting, a shape passing through the edge of a camera's glow, a movement across bait lowered into the trench. Each encounter hinted at size far beyond expectation. Over time, repeated observations confirmed what seemed impossible at first. In the deepest trenches, amphipods had grown to the scale of small mammals. These creatures carried the same basic design as their shallow relatives: curved bodies, segmented shells, limbs adapted for grasping and movement along the seafloor. Yet everything was expanded, not exaggerated, but patiently enlarged, as if size had accumulated slowly over countless generations. The trenches themselves help explain why. Hadal trenches act like biological traps. Their steep walls funnel material downward, guiding anything that sinks toward the deepest point. Organic matter that might drift away across the abyss instead slides and settles into these narrow spaces. Over time, the trench floor becomes a collection point, gathering what the ocean releases from above. This process is slow and uneven, but reliable. Gravity does the work. Currents that sweep across open plains lose their strength along the trench walls. What falls in tends to stay. In this way, trenches concentrate resources in an otherwise sparse world. Life responds to this concentration. Amphipods, already well suited to scavenging, find opportunity in these depths. They patrol the seafloor patiently, conserving energy, ready for moments when the ocean delivers something larger than marine snow. Those moments arrive suddenly. A fish dies far above and sinks. A squid fails and drifts downward. Occasionally, even larger bodies descend, carrying with them a brief abundance of food. These events are unpredictable, separated by long periods of scarcity, but when they occur, they transform the trench floor. Sudden food falls reshape survival. Amphipods swarm toward them, feeding quickly but efficiently. Those with larger bodies can consume more and store more. They can endure the long waiting periods that follow. Over time, this rhythm favors size. Larger amphipods are not faster. They do not dominate through aggression. Their advantage lies in capacity. They hold energy within their tissues. They stretch nourishment across months. They survive the silence between events. The trench environment also limits escape. Once adapted to this depth, there is little reason to leave. Pressure increases rapidly along the walls. Conditions change quickly with elevation. Life becomes specialized, anchored to the deep. The trench becomes both refuge and boundary. Isolation reinforces this pattern. Populations within a trench may remain separated from others for long spans of time. Genetic changes accumulate slowly, guided by the same pressures again and again. Size drifts upward, not in leaps, but in quiet increments. The amphipods that inhabit these depths are not monsters of the deep. They are careful products of their surroundings. Their pale bodies reflect the absence of light. Their slow movements mirror the pace of their world. Their size reflects a life built around waiting, storing, and enduring. To encounter one through a camera lens is to see a familiar creature transformed by context rather than design. Nothing new has been invented. The ocean has simply taken a small scavenger and placed it in a world where patience is rewarded more than speed. In the still darkness of the trenches, amphipods move across the seafloor with quiet purpose. They are reminders that the deepest places on Earth do not only compress life, sometimes they gather it, hold it, and allow it to grow larger than anywhere else, shaped by gravity, scarcity, and the rare gift of sudden abundance. Beyond the broad stillness of the abyssal plain, the seafloor gives way once more. It tilts, then steepens, and finally drops into narrow corridors that seem to descend without end. These are the trenches, and below their rims begins the hadal zone, the deepest living space on Earth. It is a place defined not by distance from shore, but by depth itself, where the ocean folds inward and the planet reveals one of its most secluded interiors. The hadal zone is not wide. It is long and narrow, stretching like a scar across the seafloor. Yet within this confined shape lies an entire ecosystem, shaped by conditions more extreme than anywhere else in the ocean. Pressure here is immense, pressing evenly from all sides with a force that never relaxes. Temperature remains near freezing. Light is entirely absent. Above all, isolation defines this world. Trenches are separated from one another by vast distances. Each one functions like an island turned upside down, surrounded not by water alone, but by gradients of pressure and chemistry that few organisms can cross. Moving upward changes conditions rapidly. Moving sideways is often impossible without first ascending. As a result, life within a trench becomes inward focused, shaped by long periods of separation from the rest of the ocean. This isolation slows everything. Populations remain small and stable, Encounters between individuals are infrequent. Change arrives gradually, measured across generations rather than seasons. In such a setting, life does not chase opportunity, it adapts to certainty. Pressure at these depths is not simply greater, it is absolute. There are no moments of relief. Every cell, every molecule exists under the same constant weight. Yet life persists, not by resisting this pressure, but by building itself around it. Cellular structures remain flexible. Chemical reactions continue at a steady pace. Internal spaces are filled and supported, leaving nothing to collapse. The trench environment is also shaped by gravity in a subtle way. Slopes funnel organic material downward, guiding what sinks toward the deepest points. This makes the hadal zone a place of accumulation rather than dispersal. What arrives tends to remain. Over time, this steady gathering of energy supports life that might otherwise struggle to survive. Despite its isolation and severity, the hadal zone is not empty. Microbial communities thrive in sediments, breaking down organic matter and sustaining the base of the food web. Small invertebrates move through the seafloor, feeding quietly. Larger scavengers patrol slowly, conserving energy while waiting for rare but meaningful events. Life flourishes here not through abundance, but through balance. Scarcity is constant, but so is stability. The environment changes little over time. There are no storms, no seasonal swings, no sudden shifts in temperature or chemistry. This predictability allows life to specialize deeply, refining strategies that depend on patience rather than speed. Reproduction reflects this pace. Growth is slow. Lifespans are long. Many organisms invest heavily in survival rather than rapid turnover. Each individual represents years of adaptation, finely tuned to conditions that remain consistent for millennia. The hadal zone also encourages unique relationships. Symbioses form between microbes and larger hosts. Chemical energy released from sediments is recycled efficiently. Nothing is wasted. Every available resource is used carefully, often shared across multiple forms of life. From a human perspective, it is tempting to view this depth as hostile, but hostility implies conflict. The hadal zone is not at war with life, it simply demands precision. Those who meet its conditions find a place where competition is reduced, where persistence is rewarded, and where the long view matters more than immediate success. Each trench becomes its own quiet world, shaped by the same physical laws but allowed to evolve along its own path. Over time, differences emerge. Species diverge subtly, carrying the marks of isolation in their forms and behaviors. The deep ocean, once imagined as uniform, reveals itself as a collection of distinct realms, each with its own story. As the descent settles into this deepest layer, the ocean feels less like a place of extremes and more like a place of commitment. Life here does not arrive by accident, and it does not leave easily. It takes root, adapts, and remains. The hadal zone stands as proof that even under the greatest pressure and isolation, life finds a way to persist, not loudly, not quickly, but steadily, quietly, and with remarkable success, woven into the deepest folds of the planet itself. As the descent continues into deeper water, familiar silhouettes begin to stretch into something more elusive. Squid have long occupied the human imagination, but in the deep ocean they move beyond legend and into quiet complexity. Among them, two forms stand apart, often confused but fundamentally different. The giant squid and the colossal squid share a realm, yet they represent distinct responses to life in darkness. The giant squid is defined by length. Its body extends into long, trailing arms, delicate and flexible, built to reach through open water. It is slender for its size, more ribbon than mass, its form shaped by distance rather than weight. The colossal squid, by contrast, is defined by substance. Shorter in overall length, it is far heavier, denser, and broader through the mantle. Where the giant squid stretches, the colossal squid compacts. This difference matters in the deep. As depth increases, the ocean favors bodies that can endure pressure, cold, and long intervals without feeding. Length alone offers little advantage here. Long limbs are useful for sensing and capturing prey, but mass provides something more valuable: stability, energy storage, resistance to the slow demands of the environment. Deep living squid grow heavier because weight supports survival in ways length cannot. A thicker body holds more muscle and more reserves. It stabilizes movement in still water, allowing the animal to hover without constant effort. It provides space for larger organs, including eyes built to gather faint traces of light and tissues adapted to slow metabolism. The colossal squid embodies this strategy. Its muscles are powerful but not designed for speed. They are built for brief effort followed by long rest. Its tissues are dense, reducing buoyancy swings and minimizing energy loss. Even its arms, though shorter than those of the giant squid, are thicker and stronger, equipped to hold rather than chase. This approach reflects a deep sea logic. In a world where encounters are rare, capture must be decisive. Speed is less important than certainty. When prey appears, the opportunity may not return for a long time. Yet despite their size, both giant and colossal squid remain difficult to understand. Most of what is known comes from fragments, pieces found in the stomachs of whales, bodies recovered after death, rare encounters caught briefly on deep-sea cameras. Their lives unfold almost entirely beyond observation. Their life cycles remain one of the deep ocean's quiet mysteries. Where they hatch, how they grow, and how long they live are questions answered only in outline. It is believed that they begin small, drifting as transparent juveniles near shallower depths, carried by currents before gradually descending. As they grow, they sink deeper, following a path shaped by changing pressure and food availability. Growth is likely slow and uneven. Long periods of limited intake punctuated by rare successes. Each feeding event contributes not only to immediate survival, but to long-term mass. This gradual accumulation favors bodies that can store and protect energy over time. Reproduction remains largely unseen. Mating likely occurs in deep water, but evidence is scarce. Eggs may drift upward, beginning the cycle anew, far from the depths where the adults reside. The ocean itself becomes the connective tissue of their lives, carrying each stage to a different layer before returning it downward. What is clear is that these squid are not built for constant motion. They are ambush hunters and patient travelers. Their presence is quiet, their movements are deliberate. Their size is not a display, but a solution. The contrast between giant and colossal squid reveals how the deep ocean shapes form along multiple paths. One emphasizes reach and flexibility, the other emphasizes mass and endurance. Both arise from the same pressures, yet arrive at different outcomes, guided by subtle differences in strategy and environment. This diversity within constraint is one of the deep sea's defining traits. Conditions are extreme, but they are also stable. Within that stability, life explores options slowly, testing what works across long spans of time. The colossal squid problem is not simply about size. It is about understanding how weight, shape, and mystery intertwine in a place where observation is fleeting. These animals remind us that some of Earth's largest creatures live lives almost entirely unseen, shaped by darkness, pressure, and patience rather than spectacle. They move through the deep not as monsters, but as quiet answers to an environment that rewards those who can endure, conserve, and wait. As the descent carries farther from the fading memory of light, vision does not disappear. Instead, it transforms. In a world where darkness is complete and constant, seeing becomes less about clarity and more about sensitivity. For some of the deep sea's largest inhabitants, eyes remain central to survival, not despite the darkness, but because of it. In these depths, light no longer comes from the sun, it comes from life itself. Brief flashes ripple through the water, released by drifting organisms, startled prey, or deliberate signals. These pulses are small and fleeting, often no more than a whisper against the dark, yet for those equipped to notice them, they carry meaning. Some deep sea giants invest heavily in vision because information travels farther as light than as touch or chemistry. A single glimmer can cross long distances in clear, still water where scent spreads slowly and vibrations fade. Light moves quickly and cleanly. Detecting it early offers a quiet advantage. Eyes in the deep are not built to see detail. They are built to collect. Their lenses are wide. Their retinas are packed with cells tuned to faint illumination. Each eye functions like a deep well, gathering whatever photons drift its way. Even the smallest flash, reflected or emitted, can register as presence. This sensitivity allows animals to detect bioluminescence at remarkable distances. A moving point of light may signal prey stirring nearby. A scattered shimmer may mark a cloud of small organisms feeding. A sudden burst may indicate disturbance, a collision, or an opportunity. These signals do not form images as humans know them. They form awareness. Size enhances this ability in subtle ways. Larger bodies can support larger eyes. Bigger eyes gather more light, not because they see farther in a simple sense, but because they collect more information from the darkness around them. Each increase in surface area brings more photons into the system, improving detection without demanding speed. Large heads also allow for greater separation between eyes, which can improve depth perception even in low light. This matters when estimating distance in a world where objects are rarely seen clearly. Knowing how far away something is can mean the difference between expending energy wisely or wasting it entirely. The cost of maintaining such eyes is not small. Visual tissue is expensive to build and maintain. It consumes energy constantly, even when nothing is seen. For many deep-sea creatures, this cost is too high. They abandon vision almost entirely, relying instead on touch, chemistry, or vibration. But for certain giants, the balance tips the other way. Their size allows them to absorb the cost. Their slower metabolism stretches energy use across long spans. What they spend on vision, they recover through patience and efficiency. When an opportunity finally appears, they are ready. Eyes also serve a quieter purpose. In the deep, encounters are rare. Finding a mate can take time. Bioluminescent cues, faint and specific, may help individuals locate one another across open water. Large, sensitive eyes increase the chance of noticing these signals before they fade. In this way, vision supports both survival and continuity. It does not dominate the sensory world, but it complements it, filling in gaps left by other senses. Where touch cannot reach and chemistry cannot travel quickly enough, light offers a brief connection. The eyes of deep sea giants often appear outsized when illuminated by human instruments. They seem disproportionate, almost fragile against the darkness. But this impression comes from judging them by surface standards. In their own environment, these eyes are precisely scaled, matched to the long distances and rare signals that define the deep. There is also a psychological element to vision in darkness, though it is not one of fear or awareness as humans experience it. Vision allows an organism to remain oriented, to sense movement in a vast, empty space. It anchors the body in its surroundings, even when those surroundings are almost entirely absent of features. As depth increases, the world becomes simpler in structure, but larger in scale. Eyes help navigate this openness. They do not reveal landscapes or colors, they reveal events. A flicker, a motion, a change. Size, in this context, becomes a visual advantage. Larger bodies support larger sensory systems, which in turn allow those bodies to function effectively without constant movement. Seeing first means moving less. Moving less conserves energy. Energy conserved extends survival. In the deep ocean, eyes are not relics of a brighter world. They are refined instruments, tuned to a different kind of seeing. Through them, giants read the darkness, gathering meaning from the smallest traces of light and carrying vision forward as one of the many quiet adaptations that allow life to persist where the sun has never reached. As the descent continues through the deep, another quiet influence begins to shape life in subtle but powerful ways. It is not light, nor food, nor pressure alone. It is oxygen, carried silently through cold water, present in amounts that feel modest, but prove decisive over time. Cold water has a particular quality. It holds gases more easily than warm water, allowing oxygen to remain dissolved rather than escaping back into the atmosphere. As the ocean cools with depth and latitude, this effect becomes more pronounced. Molecules slow, motion softens, oxygen lingers. In the deep sea, especially in colder regions, this steady presence matters. Oxygen fuels metabolism, even when that metabolism runs slowly. It supports the quiet chemical reactions that keep cells functioning, tissues repairing, and bodies enduring long spans of time. Where oxygen is limited, size can become a burden. Where it is reliably available, size becomes possible. Larger bodies require more oxygen in total, but not in proportion to their mass. As organisms grow, their volume increases faster than their surface area. This means that, relative to their size, larger animals can use oxygen more efficiently. Their systems lose less energy per unit of mass. Each breath, each exchange across membranes, carries them farther. Cold temperatures reinforce this efficiency. Chemical reactions slow, reducing overall demand. Muscles work at a measured pace. Growth stretches across years. Combined with steady oxygen availability, this creates an environment where large bodies can function without strain. In warmer waters, high metabolism and lower oxygen availability push life towards smaller forms. Energy burns quickly, demand rises, limits appear. In cold, deep water, the opposite pattern emerges. Demand falls, supply remains stable, constraints relax. This balance becomes especially clear in polar deep seas. Beneath ice-covered surfaces, water sinks cold and heavy, carrying oxygen downward. These regions act as reservoirs, feeding the deep with fresh, oxygen-rich water. Over long distances, currents spread this influence outward, refreshing habitats that would otherwise stagnate. In these polar depths, size amplification becomes noticeable. Crustaceans grow larger, fish develop heavier bodies, invertebrates expand beyond expectations set by warmer regions. The cold does not slow life into fragility, it stabilizes it into endurance. This does not mean that oxygen is abundant in a simple sense. Deep sea environments are still sparse. What changes is reliability. Oxygen levels fluctuate less. There are no sudden crashes tied to surface blooms or seasonal heating. The deep remains steady, and steadiness favors long-term strategies. Larger bodies benefit from this predictability. Their tissues can afford slower circulation. Their cells can operate without constant urgency. Repair replaces replacement. Longevity replaces speed. Cold also reduces the threat of overheating, a concern that grows with body size. In warm environments, large animals struggle to shed excess heat. In the deep cold, heat dissipates easily. Body temperature remains stable without costly regulation. This allows mass to accumulate without introducing new stresses. Over evolutionary time, these conditions work together. Oxygen availability supports metabolism. Cold slows consumption. Stability rewards patience. Size becomes less risky and more useful. The result is not uniform gigantism, but a gentle upward drift in potential. In places where oxygen remains low or food unpredictable, size remains constrained. In cold, oxygen-rich depths, the ceiling lifts slightly, enough to allow familiar shapes to grow broader, heavier, and longer-lived. Polar deep seas represent this effect at its clearest. They are places where multiple supportive factors align. Cold water sinks, oxygen travels with it, pressure remains constant, light never intrudes. Life there follows a rhythm shaped by consistency rather than abundance. From a human perspective, these environments seem severe. From a biological one, they are remarkably forgiving. They remove many of the stresses that limit growth elsewhere, replacing them with slow, even conditions that allow life to explore size as a viable path. As the descent continues, oxygen and cold remain quiet partners in the story of deep sea size. They do not announce themselves. They simply persist, supporting bodies that grow larger not through force, but through balance. In the deep ocean, especially beneath polar waters, size is not a sign of excess. It is a sign of harmony between body and environment, shaped by cold currents, steady oxygen, and the long patience of the sea. As the descent settles deeper still, the ocean begins to loosen its grip on familiar structure. Bones, shells, rigid frames, all the supports that once defined size and shape begin to matter less. In their place, another solution rises quietly from the dark. Bodies made not for resistance, but for yielding. This is where the jelly giants appear. Among the most striking of these are siphonophores, long, drifting forms that stretch through the water like living threads. Some grow longer than the largest whales, yet they are not single animals in the usual sense. They are colonies, composed of many individual units working together so seamlessly that they appear as one continuous being. Each unit performs a role. Some feed, some move, some reproduce. None survive alone. In the deep ocean, this arrangement offers extraordinary freedom. Gelatinous bodies do not rely on bones or hard shells. They are supported by water itself. Pressure presses evenly through them, inside and out, leaving no stress points to crack or collapse. Where rigid structures struggle under weight, soft tissues simply conform. They bend, they stretch, they endure. Because of this, Gelatinous life faces fewer mechanical limits to growth. There is no skeleton to reinforce, no joints to strengthen, no rigid frame that must scale proportionally as size increases. A jelly body can expand gradually, adding length or volume without demanding a complete redesign. Size becomes a matter of available energy and time, not engineering. Siphonophores take this to an extreme. Their bodies are not centralized. There is no single heart, no single brain. Instead, control and function are distributed along their length. Signals travel through networks rather than command centers. If one part is damaged, the whole does not fail. The colony continues, adjusting quietly around the loss. This distributed design solves one of the deep ocean's greatest challenges: fragility. In a world where encounters are rare but potentially consequential, being able to absorb damage without catastrophic failure matters. Gelatinous giants are resilient not because they are tough, but because they are redundant. Many parts perform similar roles. Failure becomes localized rather than fatal. Scaling up only enhances this advantage. A longer siphonophore can deploy more feeding units across a wider area, increasing the chance of intercepting drifting prey. Each unit works independently, capturing what passes nearby. Energy flows inward from many points rather than a single mouth. Feeding becomes passive and continuous. Movement, too, is efficient. Gentle pulses travel along the body, shifting position slowly without demanding large bursts of energy. The colony drifts with currents, adjusting its orientation rather than fighting motion. Over time, this allows vast bodies to exist on surprisingly little fuel. The deep ocean rewards this strategy. Food is sparse but widespread. A long, delicate form sweeping through water can sample more space than a compact, muscular body ever could. Instead of chasing prey, jelly giants let prey come to them. Their transparency adds another layer of advantage. Light passes through them. Bioluminescent flashes do not reflect strongly. They are difficult to see, even when illuminated briefly. This reduces attention from predators and prevents wasted energy on defense. In many ways, gelatinous giants feel less like animals and more like processes. They are living currents shaped by water, time, and chemistry. Their growth is slow and steady. Their presence is subtle, yet their scale can exceed anything built on bone. For scientists, siphonophores challenged long-held assumptions about what it means to be large. Size was once thought to require strength, structure, and central control. These organisms demonstrate another path entirely, one that replaces strength with flexibility, control with cooperation, and structure with flow. This path is especially suited to the deep ocean. Pressure supports rather than threatens. Darkness hides rather than exposes. Time stretches long enough for gradual growth to matter. Gelatinous life can scale almost infinitely because it does not fight its environment. It accepts it. It allows water to carry weight, pressure to provide support, and redundancy to replace durability. In the quiet depths, jelly giants drift, extended across the dark like living constellations. They do not dominate through force. They persist through design. Their bodies, soft and distributed, reveal a simple truth of the deep ocean. When rigidity fails, yielding succeeds. And sometimes, the largest forms on Earth are built not from strength, but from surrender. As the descent settles into its deepest rhythms, time itself begins to feel different. In the dark, far from the restless cycles of the surface, life no longer measures success in speed. It measures it in persistence. Here, longevity becomes one of the most valuable traits an organism can possess. In the deep ocean, larger animals often live longer lives. This is not coincidence. It is the natural outcome of an environment where change is slow, danger is infrequent, and energy arrives in rare, unpredictable moments. A body built to last gains an advantage simply by remaining present long enough to benefit from what eventually comes. Large bodies lose energy more slowly. Heat escapes at a gentler rate. Metabolic processes tick forward at an unhurried pace. Each stored reserve is stretched across longer spans of time. In the cold and pressure of the deep, this efficiency allows life to remain stable without constant replenishment. Growth reflects this same patience. Many deep sea animals grow slowly, sometimes almost imperceptibly from year to year. Tissue is added carefully, structures strengthen gradually. There is no rush to reach maturity because there is little benefit in doing so. Food does not reward haste, and space is rarely contested. Delayed reproduction follows naturally. Producing offspring requires energy, and in the deep, energy is precious. Rather than reproducing often, many large deep sea animals wait. They invest heavily in fewer reproductive events, spreading them across long lifespans. When conditions align, when enough energy has been stored, reproduction occurs deliberately. This strategy reduces risk. In a world where encounters are rare, flooding the environment with offspring offers little advantage. Instead, survival favors offspring that are well provisioned and released at the right moment, carried by currents that will support their early development. Longevity also allows individuals to experience multiple rare events across their lives. A fallen carcass, a seasonal shift in currents, a brief increase in food delivery from above. Those who live longer are simply more likely to be present when these moments arrive. Time becomes a resource in itself. Stability replaces speed as the central goal. Deep sea environments change little from day to day or year to year. Temperature remains constant. Pressure never relents. Darkness is complete and unbroken. Under these conditions, rapid response is unnecessary. Adaptations favor reliability rather than flexibility. Muscles are used sparingly. Movement is minimized. Repair becomes more important than replacement. Cells focus on maintenance, preserving function rather than maximizing output. This reduces wear and tear, extending lifespan further. Predation patterns also support longevity. In the deep, predators are fewer and encounters less frequent. When threats do appear, they are often avoided through stillness or distance rather than confrontation. Survival depends less on escaping quickly and more on remaining unnoticed. Over evolutionary time, these pressures shape life histories that look very different from those at the surface. Fast growth and early reproduction give way to slow development and extended maturity. The entire arc of life stretches outward, unfolding across decades rather than seasons. This does not make the deep ocean static. Change still occurs, but it unfolds gently. Genetic variation accumulates slowly. Adaptations are refined rather than reinvented. Stability allows successful traits to persist without constant testing. For scientists, this longevity complicates understanding. Long-lived animals are difficult to study. Their growth is slow. Their reproduction is rare. Entire lifespans may pass beyond human observation. Much of what is known comes from fragments, glimpses, and careful inference. Yet these long lives tell a clear story. In the dark, time favors those who endure. Speed offers little reward when opportunity arrives infrequently. What matters is being there when it does. As the descent continues, this pattern of longevity weaves through the deep ocean like a quiet thread. large bodies, slow growth, delayed reproduction. Each trait reinforces the others, forming a strategy built around patience rather than urgency. In the deep, life does not race against time. It settles into it. Stability becomes the ultimate advantage, allowing organisms to persist through long silences and brief abundance alike. And in that persistence, the dark ocean reveals one of its most enduring lessons. Sometimes, surviving longer matters far more than moving faster. As the descent continues into deeper and quieter water, the nature of danger changes. Predation does not disappear, but it becomes less frequent, more deliberate, and far more consequential. In the deep ocean, encounters are rare, distances are vast, movement is slow. When two large animals finally cross paths, the moment carries weight that surface life rarely experiences. There are fewer predators here, not because the environment is gentle, but because it cannot support many active hunters. Food is too scarce to sustain constant pursuit. Energy is too valuable to waste on frequent failed attacks. As a result, predation becomes selective. Each attempt must count. This scarcity reshapes behavior on both sides of the encounter. Predators do not roam endlessly in search of prey. They wait, they drift, they conserve strength until opportunity appears. Prey, in turn, do not live in constant flight. There is little reason to move quickly when danger may not appear for weeks or months. When predation does occur, the stakes are higher. There are no nearby shelters, no dense vegetation, no tight crevices filled with neighbors. The deep offers openness rather than refuge. An encounter unfolds slowly, often beginning with distant awareness rather than sudden surprise. In this environment, size takes on a different meaning. Near the surface, size can invite attention. It can make an animal easier to spot and harder to hide. In the deep, size often acts as deterrence rather than defense. A large body signals difficulty. It suggests effort. It implies that a predator would need to invest precious energy to succeed. Many deep-sea predators are not built for prolonged struggle. They rely on ambush and efficiency. If a target appears too large, too robust, or too uncertain, it may simply not be worth the cost. Energy spent in a failed attempt cannot easily be replaced. This is why size functions quietly, without confrontation. A large body does not need to fight. It only needs to exist. Its presence shifts the calculation before contact ever occurs. Predators weigh mass, movement, and likelihood of success long before closing the distance. Armor and weapons matter less here than persistence. Hard shells and spines do exist, but they are rarely tested. What matters more is the ability to endure long periods without interaction. Avoiding encounters altogether becomes the safest strategy. Escape, so central to surface survival, loses its urgency. Speed is expensive, and opportunities to use it are rare. Chasing or fleeing across open water burns energy quickly and offers little guarantee of success. Instead, deep-sea animals rely on stillness, distance, and time. Endurance replaces evasion. A large body can remain motionless for long spans without stress. Its metabolism continues steadily. Its energy reserves remain intact. When danger passes, it has lost little. A smaller body might survive a chase, but the cost of that escape could shorten its future significantly. Predation in the deep is often about timing rather than agility. Being present when a predator arrives is less important than being present when food arrives. Life prioritizes the latter. This does not mean that deep-sea animals are unaware of threat. Senses remain sharp. Vision, Vibration detection and chemical awareness all contribute to early detection. But once a predator is noticed, the response is measured. Sometimes it is a slow adjustment of position. Sometimes it is a simple refusal to engage. In rare moments, when contact cannot be avoided, the outcome is decisive. Struggles do not last long. One side expends energy that may not be recovered for a very long time. These events shape life histories deeply, reinforcing strategies that minimize risk above all else. Over time, this dynamic favors forms that reduce the likelihood of interaction rather than win confrontations. Size discourages pursuit. Patience avoids exposure. Longevity increases the chance of outlasting danger altogether. The deep ocean does not reward boldness, it rewards restraint. Predation remains part of the system, but it operates quietly, shaping life through absence more than presence. Most animals will go their entire lives without facing many threats, but those few encounters are enough to guide evolution toward caution, efficiency, and endurance. As the descent continues, the deep grows calmer, not because danger is gone, but because life has learned how to live alongside it without constant struggle. In this world, survival does not depend on outrunning an enemy. It depends on lasting long enough that the encounter never needs to happen at all. Far below the last traces of movement, where the ocean floor stretches wide and still, abundance does not arrive gently. Most of the time, nourishment drifts down in fragments, slow and sparse. But on rare occasions, the deep receives a gift so large that it reshapes the seafloor around it. This is the moment of a whale fall. When a whale dies at the surface, its body begins a long descent. It sinks quietly through layers already left behind, passing zones of fading light, cold stability, and patient darkness. By the time it reaches the deep, it carries with it an immense concentration of energy, gathered over a lifetime spent feeding in productive waters above. When the body settles onto the seafloor, the stillness breaks. Scavengers arrive first. Large fish, amphipods, and other deep-sea consumers gather quickly, drawn by chemical signals spreading through the water. For creatures accustomed to long waits between meals, the arrival of a whale fall is transformative. Feeding becomes immediate and intense, yet still deliberate. Energy that might have taken years to accumulate suddenly becomes available in abundance. This phase can last months. Flesh is stripped away steadily, consumed by organisms that are often built for exactly this kind of opportunity. Larger bodies benefit most. They can eat more, store more, and remain present longer. What cannot be consumed immediately is absorbed into reserves that will sustain life through long stretches of scarcity to come. As the soft tissue disappears, the event does not end. The bones remain, massive and rich in oils, locked deep within their structure. New communities assemble around them. Specialized organisms settle in, including bacteria that break down bone lipids and release nutrients slowly over time. Worms, clams, and other invertebrates depend on these processes, forming dense clusters where nothing existed before. What emerges is an entire ecosystem built not on constant supply, but on delayed release. Energy flows outward from the bones gradually, supporting life for years, sometimes decades. The whale fall becomes a long-lasting anchor of nourishment in an otherwise sparse world. For giants of the deep, these events matter profoundly. They do not rely on whale falls for daily survival, but they benefit from them across a lifetime. A single encounter can fuel growth, reproduction, and endurance long after the remains have faded into sediment. Episodic abundance complements slow living, allowing large bodies to persist where steady abundance does not exist. These rare events also influence evolution. Organisms that can locate whale falls quickly, feed efficiently, and endure long waits between them gain an advantage. Over time, traits that support size, patience, and sensory sensitivity are reinforced. The deep ocean does not reward constant success, it rewards readiness. Whale falls also connect distant parts of the ocean. Nutrients gathered near the surface are transported directly to the deep, bypassing the slow trickle of marine snow. In this way, the lives of surface giants shape the fate of deep ones, even though they never meet in life. Each whale fall leaves a subtle mark on the seafloor. Sediments change, microbial communities shift, traces of increased activity remain long after the visible remains are gone. Over geological time, these events may influence where life clusters and how populations spread across the abyss. To human eyes, the idea of an ecosystem built around death can feel stark. In the deep ocean, it is simply another form of balance. Nothing is wasted. Even the largest body becomes part of a cycle that sustains life far beyond itself. Whale falls remind us that the deep ocean is not sustained by constant abundance, but by rare generosity. These moments of plenty arrive without warning, reshape local worlds, and then fade quietly back into stillness. Life adapts by being ready, by lasting long enough to encounter them. As the descent continues, the ocean feels less empty and more interconnected. Events at the surface echo downward. Lives separated by kilometers of water remain linked through gravity and time. In the deep, giants persist not because food is common, but because the rare arrival of something vast is enough. Whale falls stand as one of the clearest examples of how the deep ocean works, not through speed or excess, but through patience, endurance, and the quiet power of waiting for what eventually comes. As the descent carries deeper into the long, narrow folds of the seafloor, separation becomes more than distance. It becomes destiny. The trenches, already shaped by pressure and darkness, begin to function as worlds apart. Each one forms a boundary that few creatures ever cross, turning depth itself into a kind of shoreline. In this sense, trenches behave like evolutionary islands, not surrounded by air and water, but by gradients of pressure, chemistry, and temperature that rise steeply along their walls. Moving out of a trench is not simply a matter of travel. It requires crossing environments that change rapidly, often beyond what a specialized body can tolerate. As a result, life that enters these depths tends to remain there. This isolation is profound. Populations within a trench may persist for thousands of years with little exchange from outside. Currents move above them, but rarely lift organisms upward. Neighbors exist, but only within the same narrow corridor of depth. Over time, this separation quiets the influence of the broader ocean and amplifies the influence of chance. In such isolation, evolutionary drift becomes a powerful force. Small differences, once insignificant, are no longer diluted by constant mixing. Traits can persist simply because they are present, not because they are optimal in every sense. The environment remains stable enough that these traits are not challenged aggressively. They are allowed to remain, to accumulate, and to shape future generations. This is how unusual forms survive. In more connected ecosystems, extreme traits are often selected against. Competition is intense, conditions shift. Anything that falls too far from the average is tested quickly. In trenches, testing is gentle and infrequent. The environment changes little. Pressure, cold, and darkness remain constant. As long as a trait does not hinder survival, it may continue quietly. Size is one of these traits. In isolated trench populations, size can drift upward over time, not suddenly, and not uniformly, but gradually. Larger individuals may store more energy. They may endure longer between rare feeding events. They may reproduce less often, but live long enough to offset that delay. None of these advantages are dramatic on their own. Together, across long spans of time, they add up. Without frequent influx of smaller, faster growing individuals from elsewhere, there is no force pulling size back toward a surface average. The population slowly shifts. Each generation carries a slightly heavier presence than the last. Over centuries and millennia, this drift becomes visible. This process does not require constant selection for size. It only requires the absence of strong pressure against it. Trenches provide exactly that. Few predators, stable conditions, limited competition. Life is not pushed to be smaller, quicker, or more efficient in the surface sense. It is allowed to be persistent. Isolation also encourages specialization. Sensory systems tune themselves to the trench environment. Metabolism settles into a slow rhythm. Reproductive strategies adjust to long waits and rare encounters. These changes reinforce one another, creating populations that are deeply adapted to their narrow world. Once such adaptations take hold, leaving becomes even less likely. A body shaped for extreme pressure and stable cold does not transition easily back into shallower water. The trench becomes not only a home, but a boundary. Over time, each trench develops its own character. Similar species diverge subtly between locations, shaped by local conditions and random variation. The deep ocean, once imagined as uniform, reveals itself as a mosaic of quiet lineages, each evolving in partial isolation. This process mirrors what happens on remote islands at the surface. There, limited space and isolation allow unusual sizes and shapes to persist. In the trenches, the same logic applies, but the forces are slower, heavier, and more patient. Evolutionary drift does not aim, it wanders. In the deep, where time stretches and change arrives softly, wandering is allowed to continue for a very long while. Size increases not because it is always better, but because nothing insists that it stop. As the descent continues through these isolated corridors, the ocean feels less like a single system and more like a collection of separate histories. Each trench carries its own quiet experiments, shaped by isolation and time. In the deepest parts of the sea, evolution does not rush, it drifts, and in that drifting, size, form, and life itself are given room to grow in directions rarely permitted anywhere else on Earth. As the descent settles into its deepest logic, a quiet correction emerges. Size has grown again and again through this journey, shaped by cold, pressure, patience, and time. Yet the deep ocean is not filled entirely with giants. Many creatures remain small, delicate, and lightly built. Their presence is not a failure of the pattern, but an essential part of it. Growth, even in the deep, carries limits. Every increase in size brings new demands. Larger bodies require more total energy, even if they use it efficiently. They need more material to grow, more time to mature, and more internal coordination to function smoothly. In environments where food arrives unpredictably, these demands can become risks rather than advantages. Some forms of life simply cannot afford to wait. Small bodies reproduce more quickly. They reach maturity sooner. They can respond faster to short-lived opportunities and sudden changes. In parts of the deep where resources arrive in brief pulses or where conditions vary subtly over time, this speed matters. A small organism can complete multiple generations while a larger one is still growing. Reproduction itself imposes trade-offs. Large animals tend to invest heavily in fewer offspring. This works well in stable environments where survival is likely once maturity is reached. But in areas where mortality remains unpredictable, spreading risk across many offspring becomes safer. Small size supports this strategy, allowing frequent reproduction with lower individual investment. Mobility also shapes the boundary of growth. Some niches require movement across wide areas, not drifting, but active searching. Smaller bodies accelerate more easily and maneuver through complex spaces. They can exploit narrow crevices, thin sediment layers, or microhabitats unavailable to larger forms. In these places, being compact is an advantage. There are also physical constraints tied to function. Feeding strategies impose limits. Filter feeders must balance intake area with water flow. Burrowing organisms must move sediment efficiently. Parasites must remain small relative to their hosts. In each case, growing larger would reduce effectiveness rather than enhance it. Energy pathways matter as well. Not all deep-sea food webs support large consumers. Some rely on microbial loops and fine-scale recycling where energy moves slowly and locally. These systems favor organisms that operate at small scales, extracting value from minute resources with precision rather than storage. Pressure and cold, while permissive of size, do not eliminate mechanical constraints entirely. Muscles still must contract, nerves must transmit signals, structures must coordinate across distance. For some designs, scaling up introduces delays and inefficiencies that outweigh the benefits of added mass. As a result, gigantism appears selectively. It emerges where conditions align, where stability is high, predation is low, oxygen is sufficient, and food arrives in a way that rewards storage and patience. Where any one of these elements weakens, the path toward large size narrows. This selectivity is what makes deep-sea gigantism meaningful rather than universal. It is not a blanket response to depth, but a specific outcome for certain strategies. Life explores size as one option among many, not as a default destination. The deep ocean remains diverse because it allows multiple solutions to coexist. Giants drift and endure. Smaller forms multiply and adapt. Both succeed, not by following the same path, but by fitting precisely into different corners of the same environment. This balance prevents any single form from dominating completely. Large animals do not overwhelm the deep because their growth is slow and their numbers are limited. Small organisms continue to form the foundation of ecosystems, processing energy, recycling nutrients, and sustaining the broader system. In this way, the deep ocean avoids extremes. It does not collapse into uniform gigantism, nor does it remain confined to tiny life alone. Instead, it maintains a layered complexity where size reflects role, timing, and strategy rather than simple advantage. Understanding why not everything gets bigger brings clarity to the pattern as a whole. Gigantism is not a goal, it is a consequence. It appears when conditions allow it and disappears where they do not. As the descent continues, this realization settles gently into place. The deep ocean is not a factory for giants. It is a patient environment that permits growth only when growth fits. In its darkness and stillness, life remains selective, measured, and balanced, allowing many forms to persist side by side, each exactly as large as it needs to be. As the descent reaches greater depth and stillness, another realization settles quietly into place. Much of what we believe we know about the deep ocean is shaped not only by what exists there, but by what we are able to see, and in the deep, seeing is never complete. For decades, The primary tools for studying deep sea life were blunt ones: nets dragged across the seafloor, trawls pulled slowly through darkness. These methods were designed for sturdier creatures, animals with shells, bones, and forms that could survive capture. Fragile bodies did not fare well. Soft tissues tore, gelatinous forms collapsed. Long, delicate organisms broke apart before ever reaching the surface. What returned in those nets was therefore incomplete. Hard bodied animals appeared common, soft giants appeared rare or non existent. The picture that formed was not wrong, but it was narrow, shaped by what could endure the journey upward. Even today, many deep sea giants leave no trace in trawls at all. Jelly like bodies disintegrate under pressure changes. Siphonophores fragment into unrecognizable pieces. Large but delicate forms vanish without record. Absence in samples does not mean absence in reality. It often means fragility. Submersibles and remotely operated vehicles brought a gentler approach, but they carry their own limits. Cameras illuminate only a small circle of water. Beyond that beam lies complete darkness. Animals outside that narrow window remain unseen, no matter how large they may be. Movement complicates this further. Many deep sea organisms drift slowly, blending with currents. They do not react dramatically to approaching lights. Some avoid them entirely. Others pass through only briefly. A single dive captures moments, not patterns. Depth itself restricts access. Most dives last hours, not days. Entire lifespans unfold between visits. Rare events, such as feeding aggregations or reproductive gatherings, are easily missed. What we observe becomes a collection of glimpses stitched together across years. Cameras also change behavior. Artificial light introduces something foreign into a world that has never known it. Some animals retreat, others approach out of curiosity or confusion. What appears on screen is already filtered by response to intrusion. Even when sightings occur, scale can be deceptive. Without reference points, size is difficult to judge. A long body drifting past a camera may appear smaller or larger than it truly is. Distance and perspective blur understanding. Measurements often rely on estimates rather than certainty. There is also the problem of rarity. Many deep sea giants exist at low densities. They may occupy vast territories, encountering one another only occasionally. The chance of crossing paths with a submersible during a brief survey is small. Entire species may remain unseen simply because timing never aligns. This means that our current picture of deep sea size is likely conservative. We know of giants because some reveal themselves often enough to be noticed. Others may exist beyond our instruments, passing through darkness without ever crossing a lens. The deep ocean covers most of the planet, yet only a tiny fraction has been observed directly. Even within studied regions, observation is uneven. Trenches, slopes, and plains each present different challenges. Some areas are revisited frequently, others remain unexplored for decades. What remains unseen is not necessarily rare, it is simply unobserved. This uncertainty shapes interpretation. Patterns we detect are real, but they may be incomplete. Deep sea gigantism may extend farther across lineages than currently documented. The balance between small and large forms may look different when fragile giants are fully accounted for. Scientific understanding advances cautiously in this environment. Claims are measured, conclusions remain provisional. Each new observation has the potential to reshape what seemed settled. In recent years, improved imaging, longer deployments, and quieter technologies have begun to reveal more of what was missed. Extended camera landers capture life over days rather than hours. Low light sensors reduce disturbance. Slowly, the picture expands. Yet, even with these advances, the deep remains mostly unknown. There are depths where no camera has lingered, spaces where no net has passed gently enough to preserve what lives there, forms that may never interact with our tools at all. This is not a failure of science, it is a reminder of scale. The ocean is vast beyond easy comprehension. Life within it is adapted to conditions that resist observation. What we know is shaped by patience, limitation, and humility. As the descent continues, this awareness becomes part of the story itself. The giants we have met may not be the largest. The patterns we see may not be complete. In the deep, absence of evidence is not evidence of absence. It is simply silence. And in that silence, much of life continues, unseen, shaping the ocean in ways we are only beginning to sense. As the descent continues, another quiet challenge comes into focus. Even when the deep ocean reveals something remarkable, it rarely does so twice. Many of the giants encountered so far appear briefly, then vanish back into darkness, never to be seen again. This is not because they disappear. It is because the deep is vast, and encounters are rare by nature. In the deep ocean, space stretches far beyond the reach of any single observation. Distances are immense. Movement is slow. Populations are spread thinly across enormous areas. An animal can live its entire life without crossing paths with another of its kind, let alone with a camera lowered from the surface. When a giant drifts into view, it is often the result of chance rather than predictability. This is why so many deep-sea giants are known from a single sighting. A brief pass through a cone of light, a silhouette moving at the edge of visibility, a shape recorded once and never again. These moments feel incomplete, but they are honest reflections of how the deep operates. Estimating populations under these conditions becomes extraordinarily difficult. On land, scientists can count tracks, nests, or repeated sightings. In shallow water, reefs and coastlines offer fixed reference points. In the deep, there are no landmarks in the same sense. The seafloor may stretch uninterrupted for hundreds of kilometers. Water above it flows slowly, carrying life without leaving obvious traces. When an organism is seen only once, it raises careful questions about abundance. Is it rare or merely elusive? Does it exist in low numbers, or does it occupy a wide range at low density? Without repeated encounters, answers remain tentative. Many deep-sea giants likely exist in numbers too small to form clusters. Their life strategies do not require proximity. They do not gather in herds or schools. They drift, patrol, or wait alone. This solitude reduces competition, but it also reduces the chance of observation. Time adds another layer of difficulty. Deep-sea lifespans are long. Reproduction is infrequent. Growth is slow. A population may remain stable for decades without producing noticeable changes. Short research campaigns, measured in days or weeks, capture only a fraction of this timeline. As a result, science in the deep is built on glimpses rather than continuous records. Each dive adds a fragment, each image contributes a piece. Over years and decades, these fragments begin to form patterns, but the gaps between them remain large. This does not make the science weak, it makes it cautious. Researchers learn to work with uncertainty. They compare sightings across regions. They look for recurring shapes, similar proportions, familiar movements. They use indirect evidence, such as feeding marks, sediment disturbance, or chemical signatures, to infer presence even when bodies are unseen. Even so, Many giants remain statistical ghosts, known to exist, but not known well. Their ranges are guessed, their numbers are approximated, their behaviors are inferred from anatomy rather than observed directly. Technology continues to improve, but it cannot eliminate rarity. Longer deployments increase the chance of encounter, but they cannot force one. Cameras cannot search everywhere at once. Submersibles must choose paths through vast spaces, leaving most areas unvisited. This means that absence of repeated sightings cannot be taken as absence of life. It reflects the scale mismatch between human observation and deep ocean reality. We are brief visitors. The deep is patient. In some cases, a single sighting is enough to reshape understanding. One glimpse of a massive gelatinous form can expand known limits of size. One recording of a rare behavior can challenge long-held assumptions. These moments carry weight far beyond their duration. The problem of rare encounters also shapes how stories of the deep are told. Certainty is replaced with suggestion. Confidence is tempered with openness. Each observation is treated as part of a larger, unfinished picture. As the descent continues, this awareness becomes part of the experience itself. The deep ocean is not withholding, it is simply vast. It reveals itself slowly, on its own terms, offering brief windows rather than sustained views. Science here advances not through repetition, but through accumulation, glimpse by glimpse, shape by shape. Over time, these moments begin to connect, forming a quiet mosaic of life lived mostly unseen. In the end, rare encounters do not diminish the reality of deep-sea giants, they emphasize it. They remind us that some forms of life exist at scales and densities that resist easy study, and that understanding the deep requires patience equal to its depth. The giants are there. They move through darkness whether or not we watch, and our knowledge grows not because we see them often, but because each rare meeting adds another piece to a story still unfolding. As the descent moves deeper still, the story begins to brush against a quiet absence, not an absence of life, but an absence of evidence. The deep ocean holds its history lightly, and much of what has lived there has left little behind. When we look for fossils in the deep, we often find silence. Fossilization is a rare gift anywhere on Earth, but in the deep sea it is especially unlikely. Many deep-sea organisms are soft-bodied, gelatinous, or lightly structured. When they die, their bodies are consumed quickly or dissolve into the surrounding water. There are no sturdy bones to sink and settle, no shells thick enough to resist decay. What once lived is recycled almost immediately. Even when hard parts exist, conditions do not favor preservation. The deep seafloor is active in subtle ways. Sediments move slowly, chemical processes continue steadily. Organic material is broken down efficiently by microbes. Over time, traces fade. What remains is scattered, altered, or erased entirely. Because of this, the fossil record of the deep ocean is thin and uneven. It captures fragments rather than stories. A tooth here, a shell there, rare impressions preserved under unusual conditions. Entire ecosystems leave no clear mark at all. This absence creates a distorted sense of time. When we look at fossils, it can seem as though certain traits appeared suddenly or recently. In reality, they may have existed for vast spans of time without leaving recognizable evidence. Deep-sea gigantism may not be a modern phenomenon at all. It may be ancient, recurring quietly whenever conditions allowed. The deep ocean itself has been stable for a very long time. Pressure, cold, and darkness have shaped life there across millions of years. While surface environments shifted with climate, continents, and mass extinctions, the deep changed more slowly. This stability would have allowed certain body plans and strategies to persist far beyond what the fossil record suggests. Gigantism could have emerged and disappeared multiple times, leaving little trace each time. Soft bodied giants would have lived, fed, reproduced, and vanished without imprinting their existence into stone. Their absence from fossils does not mean they were absent from history. What fossils do preserve tends to favor shallow environments. Coastal sediments accumulate rapidly. River deltas bury remains quickly. Reefs trap skeletons and shells. These settings dominate our understanding of past life, not because they were more important, but because they were more likely to record what passed through them. The deep ocean, by contrast, records almost nothing. Its memory is chemical rather than structural. Energy flows are recycled, bodies become food. Even large remains are broken down and dispersed over time. This creates gaps in Earth's biological record that cannot be easily filled. There are entire lineages we may never know, entire experiments in form and size that left no fossil descendants, evolutionary paths explored and abandoned without a trace. Scientists work around this absence by comparing living organisms, studying genetics, and modeling ancient environments. Patterns observed today offer clues to what may have existed before. If certain conditions consistently favor larger bodies now, it is reasonable to imagine they did so in the past as well. In this way, living giants become living fossils of a sort, not because they are unchanged, but because they reflect long-standing solutions to persistent conditions. Their existence hints at a deep continuity that the rock record fails to capture. This understanding brings humility to the study of life's history. What we know is shaped as much by preservation as by reality. The fossil record is not a complete archive. It is a partial one, biased towards certain places, certain bodies, and certain moments. The deep ocean reminds us of this limitation more clearly than any other environment. It holds vast stretches of time without leaving marks we can read. Its history is written in processes rather than artifacts. As the descent continues, the story of deep-sea gigantism stretches backward beyond visible evidence. It becomes less about when something first appeared and more about how often conditions allowed it to return. Size may have risen quietly many times, supported by cold, pressure, and patience, only to fade again without record. What fossils cannot tell us is not a failure of knowledge, but a boundary. Beyond that boundary lies a deeper history, one carried forward not in stone, but in living forms that still move through darkness today. The deep ocean keeps its past close, and while we may never see most of it, its influence remains, shaping life in the present and reminding us that much of Earth's story has always unfolded beyond our view. As the descent settles into its deepest layers, the story begins to stretch backward as well as downward. The deep ocean does not exist only in space, it exists in time. Conditions found in modern trenches echo environments that once covered much of the planet when Earth itself was younger, quieter, and slower to change. Ancient oceans were not like the seas we know today. They were often darker, colder in places, and more stable over long spans of time. Sunlight reached shallower depths, circulation moved differently, oxygen levels shifted gradually rather than abruptly. For long intervals, large regions of the ocean remained relatively unchanged, allowing life to adapt without constant disruption. In these ancient waters, many of the same pressures seen in today's deep sea were present. Limited light, sparse but steady food supply, few large predators, long stretches without disturbance. Life unfolded at a measured pace, shaped less by competition and more by endurance. Modern trenches recreate many of these conditions in miniature. They are isolated, they are stable, they experience little seasonal change. Pressure and cold remain constant. Once life adapts to these depths, the environment changes very little across generations. This is where deep time meets deep water. Gigantism may re-emerge under such conditions, not because size is favored universally, but because stability allows it to persist. In environments that change rapidly, large bodies become liabilities. They grow slowly, they reproduce infrequently, they struggle to adapt quickly. But in stable systems, those weaknesses soften. Time becomes an ally rather than a threat. Ancient oceans offered that kind of stability for long periods. Without frequent mass extinctions, rapid climate shifts, or intense competition, certain lineages could explore size gradually. Large forms could persist simply by surviving well enough, long enough. Modern deep sea environments provide a glimpse of how this process might have unfolded. In trenches and abyssal plains, life experiences fewer interruptions. Change arrives slowly. Evolution drifts rather than sprints. Under these conditions, traits like large size, long lifespan, and slow reproduction can remain viable. This connection helps explain why deep sea gigantism feels familiar in a geological sense. It does not appear as something entirely new. It feels like a recurrence, a resurfacing of an old solution that fits a familiar problem. Deep time is filled with gaps where soft-bodied giants may have lived and vanished without leaving fossils. The absence of evidence does not negate their presence. It simply reflects the limits of preservation. When conditions align again, similar forms may reappear, shaped by the same pressures that once guided their ancestors. In this way, the deep ocean acts as a kind of time capsule, not frozen, but slowed. It preserves environmental conditions that surface ecosystems moved past long ago. Life within it carries strategies that once may have been widespread. The parallels extend beyond size: slow growth, delayed reproduction, low population density. These traits are common in deep-sea organisms today, and they likely characterized many ancient marine lineages as well. The deep does not invent these strategies, it maintains them. Studying modern trenches allows scientists to observe processes that once unfolded across entire oceans. It offers a living window into how life responds when change is rare and time stretches wide. Patterns that appear unusual today may have been ordinary in the past. This perspective reframes gigantism not as an anomaly, but as a recurring response. When environments stabilize, when disturbance lessens, when energy flows slowly but reliably, life explores size again, not explosively, but patiently. Deep time and deep water meet in this shared logic. Both reward persistence over speed. Both allow gradual change to accumulate. Both favor forms that can endure long spans without constant adjustment. As the descent continues, the deep ocean feels less isolated from Earth's history and more like a continuation of it. The giants moving through darkness today may resemble forms that once drifted through ancient seas, shaped by the same quiet forces. This does not mean the past is repeating itself exactly. Life never retraces its steps fully, but it often rhymes. Similar conditions invite similar outcomes, even when the cast of characters has changed. In the stillness of the deep, time folds inward. The present touches the past, and through that connection, the deep ocean reveals itself not just as a place beneath the surface, but as a bridge across Earth's long and patient history, where ancient possibilities remain alive, waiting and quietly unfolding once more. As the descent continues, the deep ocean begins to feel less mysterious and more deliberate. Beneath the silence lies a quiet arithmetic, a set of relationships that govern how life uses energy. Size, once seen only as shape or presence, reveals itself as a calculation. In the deep, survival is written in careful math. In biology, bodies follow scaling laws. These are simple relationships that describe how size affects function. As an organism grows larger, its volume increases faster than its surface area. This means that a bigger body holds much more mass relative to the area through which it exchanges heat, oxygen, and energy with its surroundings. The consequences of this are subtle but powerful. Larger bodies lose energy more slowly. Heat escapes at a gentler pace. Chemical reactions inside cells proceed steadily rather than rapidly. Each unit of tissue costs less to maintain than it would in a smaller body. Energy stretches farther, lasting longer between meals. In the deep ocean, this efficiency matters more than speed or strength. Food arrives slowly. Long periods pass with little nourishment. An organism that burns energy quickly risks starvation. One that burns it slowly can wait. This is where size becomes an advantage. A large animal can store energy in muscle, fat, and tissue, not for days, but for months or even years. When food finally appears, that energy is replenished and redistributed carefully. Nothing is wasted, everything is conserved. Scaling laws also shape movement. A large body moving slowly uses surprisingly little energy per unit of mass. In still water, inertia works in favor of the animal. Once in motion, it can glide or drift with minimal effort. Smaller bodies, by contrast, must move constantly to remain stable or responsive, spending energy more frequently. The deep ocean rewards this calm momentum. Currents are gentle, space is open, there is little need for rapid acceleration or constant correction. A large form can exist almost at rest, adjusting position only occasionally, letting physics carry much of the load. Respiration follows the same logic. While larger animals need more oxygen in total, they use less oxygen relative to their size. Their tissues operate efficiently. Their metabolic rates are lower per unit of mass. In cold, oxygen-rich deep water, this balance becomes sustainable. Over time, this efficiency compounds. Energy saved today becomes survival tomorrow. A body that loses energy slowly can afford long lifespans, delayed reproduction, and patience. Each of these traits reinforces the others, forming a stable strategy. This does not mean that bigger is always better. The energy math must still balance. If food becomes too scarce or oxygen too limited, even efficient bodies struggle. But where conditions allow, size becomes a way to smooth out uncertainty rather than eliminate it. In the deep, uncertainty is constant. What changes is how it is managed. Smaller animals manage uncertainty through speed and numbers. Larger ones manage it through efficiency and storage. Both approaches can succeed, but they suit different niches. The giants of the deep embody the long view. Their bodies are not built for quick returns. They are built for slow accumulation. Each meal contributes to a reservoir that supports long stretches of quiet. Each movement is weighed against cost. This energy math also explains why deep-sea giants often appear calm and unhurried. There is no benefit in rushing. Speed burns fuel without guarantee of reward. Efficiency, by contrast, always pays. The deep ocean becomes a place where physics and biology align. Cold slows reactions. Pressure stabilizes structure. Size reduces relative loss. Together, these factors create an environment where large bodies can function with remarkable economy. As the descent continues, this arithmetic hums beneath the silence. Every organism is solving the same equation, balancing intake against loss, storage against use. Those that solve it well persist. Those that do not fade quietly into the system that feeds others. Survival in the deep is not about excess, it is about balance. Scaling laws provide the framework, but it is life that fills in the details, exploring how far efficiency can be taken without tipping into fragility. In this way, the giants of the deep are not extravagant, they are economical. Their size is not wasteful, it is precise, tuned to an environment where every unit of energy matters. The energy math of being big reveals one of the deep ocean's simplest truths. When resources are rare and time is long, efficiency becomes strength. And sometimes, the most efficient way to survive is to grow large enough that the world cannot easily drain you away. As the descent reaches its quietest depths, a simple truth settles gently into place. Humans do not belong here, not as participants, not as neighbors, and not as influences that shaped what lives below. The giants of the deep evolved without us in mind, in a world that unfolded long before our first tools touched stone. For nearly all of Earth's history, the deep ocean existed without any awareness of human presence. Its rhythms formed under pressure, darkness, and time spans that stretch far beyond our memory. Life there adapted to currents, chemistry, gravity, and scarcity, not to observation or interference. Every large form that drifts through the abyss today carries a lineage shaped entirely by forces we never experienced. Our arrival in the deep is recent and fleeting. We descend encased in metal and glass, surrounded by light and sound that do not belong. We stay briefly, collect images, measure what we can, and then retreat upward. The environment closes behind us, unchanged. Deep sea giants are not cautious because of us. They are not hidden in response to danger we present. Their slow movements, sparse populations, and quiet lives existed long before our curiosity reached them. They evolved for an ocean that asked nothing of speed, spectacle, or interaction. The deep ocean functions as a parallel biosphere. It follows the same physical laws as the surface, yet expresses them differently. Energy moves slowly. Life strategies emphasize patience over competition. Stability outweighs adaptability. In many ways, this biosphere runs alongside our own without intersecting it. Surface life is shaped by light, seasons, and rapid change. The deep is shaped by constancy. While storms reshape coastlines and climates shift across continents, the abyss remains largely the same. Its inhabitants do not track the sun. They do not migrate with seasons. Their lives unfold in a steady, unbroken dark. This separation means that deep sea giants are not responses to surface events. They are outcomes of an environment that rarely notices what happens above. Even dramatic surface changes reach the deep slowly, diluted by distance and time. When we enter this world, we do so briefly. Our presence is measured in minutes. A submersible touches down, lights turn on, cameras roll. Then the ascent begins. For the organisms that live there, this interruption is momentary, like a passing shadow. We cannot stay long enough to matter. Pressure limits our exposure. Cold drains heat. Distance restricts rescue. The deep enforces boundaries that technology can only partially overcome. These boundaries preserve the independence of its ecosystems. Because of this, deep sea giants remain largely untouched by human influence. They do not alter their behavior in response to us in any lasting way. They do not reorganize their lives around our presence. When we leave, their world returns to stillness. This does not mean the deep is fragile. It means it is separate. It operates on scales that dwarf our timelines. Its processes continue whether or not we observe them. Understanding this separation changes how the deep is perceived. It is not a frontier awaiting discovery in the way land once was. It is a vast system that will never fully accommodate us. We can observe, but we cannot participate. This distance also brings humility. Our knowledge is partial. Our influence is minimal. Our interpretations are shaped by short visits and limited perspectives. The deep ocean reminds us that not all of Earth revolves around human presence. The giants that live there are not symbols or warnings. They are not relics waiting to be uncovered. They are simply life forms that solved a different set of problems than we did. As the descent slows and the story nears its quiet end, this realization becomes comforting rather than unsettling. There is something reassuring about a world that exists beyond our reach, governed by its own rules, unfolding without reference to us. The deep ocean continues its work in darkness. Giants drift, energy circulates, time passes. And we, brief visitors from above, remain outsiders, allowed only short glimpses into a biosphere that does not need us to continue being exactly what it is. As the descent slows and the story gathers its threads, the pattern returns into view, not as a revelation, but as a presence that has been quietly shaping every layer along the way. Depth, pressure, cold, scarcity, and size have moved together throughout this journey, never perfectly aligned, yet rarely separate. Each has played a role. None has acted alone. Depth sets the stage. As distance from the surface increases, light fades, movement softens, and time stretches. With depth comes pressure, a constant force that presses evenly on every surface, asking life to adapt not through strength, but through balance. Cold settles in alongside it, slowing reactions, conserving energy, and stabilizing conditions over long spans. Scarcity follows naturally, shaping behavior around patience rather than pursuit. And then there is size. Again and again, larger bodies appear where these forces overlap. Not everywhere, not in every lineage, but often enough to form a recognizable trend. Large forms drift where food arrives slowly. Heavy bodies persist where energy must be stored and spent carefully. Long lifespans unfold where the environment remains steady. Yet, when the pattern is examined closely, it refuses to resolve into a single explanation. Pressure alone does not create giants. Many pressured environments support only small life. Cold alone does not guarantee growth. Some cold waters remain filled with delicate forms. Scarcity can favor small bodies as easily as large ones, depending on timing and flow. Even depth itself is not decisive. Similar depths can host very different communities. Each factor contributes, but none dictates. What emerges instead is a convergence. When depth brings stability, when pressure supports rather than restricts, when cold slows the pace of life, when food arrives rarely but in meaningful amounts, and when competition remains low, size becomes viable. Not inevitable, but possible. This is why deep-sea gigantism appears across unrelated groups. It is not inherited from a single ancestor. It arises independently, again and again, wherever conditions quietly align. Different lineages arrive at similar outcomes by different paths, guided not by a shared blueprint, but by shared constraints. The pattern remains visible because the environment remains consistent. Trenches and abyssal plains do not change quickly. Their rules persist across generations. Life that fits those rules is allowed to continue, refine itself, and sometimes expand in scale. At the same time, the pattern remains incomplete. Many deep sea organisms remain small, quick, or fragile. They thrive alongside giants, filling niches that size cannot reach. This coexistence reinforces the idea that gigantism is not a destination but an option among many. Attempts to isolate a single cause always fall short. Each explanation captures part of the truth, but not the whole. Energy efficiency explains endurance, but not form. Oxygen availability supports metabolism, but not behavior. Isolation allows drift, but does not dictate direction. Stability enables persistence, but does not guarantee growth. The deep ocean resists simple answers because it operates through accumulation rather than triggers. No moment flips a switch. No single variable dominates. Change unfolds slowly, shaped by many small advantages adding together over time. This is why the pattern feels real but elusive. It can be described, observed, and revisited, yet never fully pinned down. It behaves less like a rule and more like a tendency, a quiet leaning of life towards certain outcomes when circumstances allow. As the journey nears its end, this uncertainty does not weaken the story, it strengthens it. It reminds us that nature does not always offer clean explanations. Some patterns persist not because they are driven by a single cause, but because they are supported by many. The deep ocean teaches this lesson gently. It does not announce conclusions, it allows them to emerge gradually, layered across depth and time. The pattern of growing size remains. It has been seen often enough to be undeniable, but its cause remains distributed, spread across pressure, cold, scarcity, isolation, and patience. Remove any one element, and the outcome shifts. In the quiet darkness below, life does not follow a formula. It follows conditions, and when those conditions hold steady long enough, they allow something remarkable to happen, not because it must, but because nothing stands firmly in its way. The pattern remains. The cause does not settle, and in that unresolved space, the deep ocean continues to shape life in ways that are consistent, subtle, and endlessly patient. As the descent reaches its natural resting point, the ocean no longer feels like a place we are moving through. It feels like a presence we are sitting within, vast and steady, unfolding at its own pace. What remains is not a conclusion, but a quiet realization, one that settles gently rather than announcing itself. Earth's largest habitat follows different rules. The deep ocean is not a harsher version of the surface world. It is not simply life pushed to extremes. It is a parallel system, shaped by pressure, cold, darkness, and time in ways that soften urgency rather than sharpen it. Where the surface rewards speed, flexibility, and rapid response, the deep rewards patience, balance, and endurance. Here, pressure does not crush life into smaller forms, it smooths it. Cold does not freeze progress, it slows the tempo until efficiency becomes more valuable than force. Scarcity does not eliminate possibility, it reshapes it, favoring strategies that wait rather than chase. Across this journey, size has appeared again and again, not as a spectacle, but as a solution. Large bodies drift where smaller ones might burn out. Heavy forms store what little arrives and stretch it across long spans of quiet. Growth becomes gradual, lifespans lengthen, and survival aligns itself with time rather than motion. This runs against the instinct many of us carry. We expect pressure to limit, to compress, to reduce. We imagine darkness as a narrowing of opportunity. Yet in the deep, these forces combine not to shrink life, but to stabilize it. Life does not always shrink under pressure. Sometimes, pressure removes the chaos that would otherwise tear growth apart. Sometimes, cold preserves instead of destroys. Sometimes, isolation protects rather than traps. In those moments, life is allowed to explore size without being punished for it. The giants of the deep are not mistakes. They are not accidents waiting to be explained away. They are the natural outcome of an environment that has remained steady long enough for slow advantages to matter. Their size is not excess, it is balance made visible. At the same time, the deep does not become a kingdom of giants alone. Small lives persist alongside large ones, each filling roles shaped by energy, timing, and opportunity. This coexistence is part of the deep's quiet intelligence. Nothing dominates completely. Nothing is rushed out of place. What makes this realization powerful is not just what it tells us about the ocean, but what it tells us about life itself. Evolution is not always driven by competition or urgency. Sometimes it is guided by stillness. Sometimes it moves forward by waiting. In the deepest darkness, where change arrives slowly and disturbance is rare, life has room to grow in directions that surface environments no longer allow. The deep becomes a refuge for strategies that depend on time, on efficiency, and on persistence across generations. And yet, for all that has been revealed, understanding remains incomplete. Much of this world has never been seen. Many forms pass through darkness without ever crossing a lens. Many histories have left no fossil trace. What we know is built from glimpses, patterns, and careful inference. We are only beginning to understand why size emerges where it does, why it fades elsewhere, and how many paths remain unexplored. Each descent adds a little clarity, but also a reminder of scale. The ocean is vast beyond our routines. Its timelines stretch beyond our patience. Still, there is something quietly comforting in this uncertainty. It means discovery is not ending. It means the deep has not given up its secrets all at once. It means Earth still holds systems that operate beyond our assumptions. Sometimes, in the deepest darkness, life becomes vast instead of small. Not loudly, not dramatically, but patiently, layer by layer, generation by generation, guided by rules that feel foreign only because we do not live by them. As we linger at the edge of this understanding, the ocean remains below us, unchanged by our curiosity, continuing its slow work. Giants drift, small lives pulse, energy circulates. Time moves forward without urgency. And somewhere beneath the surface of what we know, the deep continues to remind us that life is not bound to one way of surviving. Under the right conditions, even in darkness and pressure, it can grow broader, heavier, and longer lived than we ever expected. We are only beginning to understand why.